Welcome everyone to my keynote on 3 challenges in building industrial scale recommender systems. Before we start, I would first like to say thank you to the organizers for inviting me for this keynote. It's a huge honor for me. And I'm going to tell you a little bit about my background. I'm an assistant professor at the University of Amsterdam with a focus on data management for machine learning. So basically for the problems that occur at the intersection of data management and machine learning. I'm also a research fellow at Untitled, a large retailer based in the Netherlands, where we have an industry collaboration on AI problems that occur in retail. Other than that, I'm also the founder of the workshop on data management for end-to-end machine learning, DEAM, at ACM Sigmod that I've been running for the last years. And previously, I've been at New York University and at Amazon Research. In the beginning of my scientific career, I worked on recommender systems much more. I've built a recommender system at Zalando and at Plista. I interned with the recommender systems team at Twitter, and I implemented some of the algorithms in Apache Mahout. And basically, in the last month, I'm starting to get back to recommender systems, and I've been very happy about this keynote invitation that gives me the opportunity to share my thoughts with you. So my talk is basically divided into 2 parts. I'm first going to talk about the challenges that we face when we bring machine learning into production. And I will try to convince you that this is actually a research problem. And that basically gives an overview over the research area that I've been working on in the last years. And then in the second part of the talk, I'm going to focus on online recommender systems. And I'm going to discuss 3 challenges that I see there if we want to build online recommender systems that are deployable in an industry. And I'm going to give you some of my thoughts there and some of the directions that we're working here in our group. But first, let's start with the general challenges. So in the last years, we've all seen, if we followed the news, we've seen an astonishing progress in machine learning. We've seen that machines now manage to beat us humans in more and more games like Go or Jeopardy that we thought to be our domain. We have seen huge advances in computer vision, and computer vision is now being deployed in the real world. So in some airports, you can board your plane via facial recognition, and there are many expectations for autonomous or semi-autonomous driving that is also based on these advances in computer vision. And in general, what we see is that more and more decisions are being automated with machines and with machine learning techniques. And what you can also observe is that often there's kind of a gold rush mentality and also machine learning arms race in industry. So all the big cloud vendors have now machine learning services in their platform. There's a huge battle in hiring machine learning talent. So there's a lot of technological progress happening here. But there's also another side, and if we look beyond the hype, then we see that this rapid progress in machine learning is also accompanied by a set of serious technical and societal problems. So in my opinion, the most crucial technical problem is that if we talk to people, to data scientists who actually do this work in the real world, then surveys always find that data preparation and data wrangling accounts for 80% of the work that these people have to do. So it's really crucial. We train these people in statistics and machine learning, and then most of their time, basically 4 out of 5 days per week, they have to prepare and clean data. So that's a waste of energy and a waste of resources. And for me, that's also a wake-up call for the systems and data management community, which means we simply need to build better and smarter systems. There's other issues. So some famous venture capitalists are starting to challenge the economics of AI, and in general, many of the new techniques like deep learning models provide astonishing results, but are very difficult and very expensive to put into production. And then there's another route. What we also observed in the last years is that we start to automate decision-making with machines and machine learning. And what happens is that in many cases, we reproduce and amplify the biases and discrimination that already exists in the world. And there's many, many examples for this. A very prominent example is that facial recognition doesn't work well for people with darker skin, for example. And the question is now, and that's also at the core of my research, what can we do to tackle these problems? And I think what helps is to take a look into the past, a look into another period in time where there was a huge technological shift that also changed the world as a whole and also had implications on how society changed, the Industrial Revolution. So it's really interesting that, for example, it took 50 years for electricity and electrical motors to revolutionize manufacturing. So the technology was invented, the research was there, but it still took 50 years until it had a real-world impact in manufacturing. What needed to happen there was technology needed to be adapted. You needed to kind of reinvent how factories worked so that they can benefit from electricity, and you needed to reorganize the production process. And in this period, these new technologies also were very dangerous. They were really dangerous to the lives of people, especially to workers who worked in these factories. And it required a combination of technological efforts to make the technology more safe, and also legislative efforts to basically force factory owners to provide more safe working environments to mitigate these issues. And I think that we are at a similar point with machine learning. So we have all these great results in research, and we have a lot of problems once we decide, once we try to put these technologies into production. And an interesting observation is shown in this figure here. That's from a famous paper that Google wrote a few years ago, where they talk about the hidden technical debt in machine learning systems. And they basically say that the actual machine learning code, the training of your model, is only a very small part, that tiny black box there, inside a much bigger system and a much bigger pipeline. And there are all these orthogonal problems that have to be solved. And many of them are related to the data and the systems and the operation of them. So I think we need to adapt this technology from ML research into production settings. And we need to take inspiration from data management research, basically relational databases and related technologies have been in production for decades already, and there's a lot of things that we can learn from that. And also from established practices in software engineering. So professional software engineering is very good in testing and integrating their technologies. So I think, and that's also at the core of my research, we need to reinvent how we validate data, how we unit test, not only conventional software, but machine learning applications, how we monitor these systems so that we can detect when something is going wrong. And that's especially, monitoring is especially difficult for machine learning systems because they can basically have silent failures. So it can be that your system doesn't crash, but it simply doesn't give the right answers. And in general, I think we need to look at end-to-end applications. And then for looking at fairness and accountability, I think the most important insight there is that's not only a technical problem. It's a socio-technical problem. It's not a problem that computer scientists can solve on their own. I think there we really need to work hand in hand with experts from other domains, such as law experts and social scientists. And I'd like to give you a bit more details, what I mean when I talk about the difference between research and production. And so on this slide, I tried to list what I think is the mental model that we have when we do research in a lab, and what's the mental model that we face once we go into production deployments. So I think in the lab, when we think about machine learning applications, we always have this mental model of working in a Jupyter notebook. So we are in control of the model, we are in control of the training process, we can look at the data. The data is usually static. Often we work with one of many famous benchmark data sets. It's relatively clean and it's relatively well understood. And also it fits into memory. So we can, for example, load it into pandas, look at it, plot all kinds of things. And also importantly, often when we do academic work, we assume that the person on the other side who judges the results of our work or who uses the frameworks or the models that we produce also has a PhD in ML. So basically, experts build software or solutions for other experts. And I think in many cases, as soon as you go to industry, to real world deployments, you see that many of these assumptions simply don't hold, and the world is much more complicated, unfortunately. So for example, the data with which you have to work in real world deployments is usually never static. So this data is usually continuously produced. It's also never clean. So there will always be errors in the data, and these errors can be very subtle. It can simply be that you have to consume data from another system, and somehow the system is changed by someone. They change the schema of the data, things like that, and it's very, very hard to avoid these data errors to have an impact on your application. Then usually we don't work with one data set. Usually the data that we consume comes from many different sources. And in general, the data that we consume is also not under our control. As I already mentioned before, very often model training is only one piece of large complex pipelines. It's not only that there are more steps for training a model, it's also typically that systems have two parts. There's usually an offline part that trains the model, and then there's an online part where the model is served, where new data is collected, and they have lots of feedback loops. So it's a complicated world. Another thing is that very often we have non-machine learning experts as end users or operators. So I think in many cases, the people who build systems might be software engineers who have a background in data science, who took some online courses, but they are not academics who have a PhD in machine learning. So they need solutions that are more tailored towards general engineers. And also there's a second class of users, that's the people who operate real-world systems. They're often called DevOps engineers. And these people are probably also not machine learning experts. And we need to be able to build systems that allow them to easily operate these systems. And then when they get paged on the weekend because something is going wrong, they need to be able to take action and fix these problems. And very often in the real world, there's also a focus beyond predictive performance. In research, we need something that we can measure so that we can compare our results. And often that's just the prediction performance for some given metric on held out data. But in production, there are many orthogonal aspects that are as important, like the scalability of our solutions, how simple it is so that we can change and maintain it, the response times of our system so that provides a good user experience, and also things like the debuggability, like how difficult it is to inspect a solution if something is going wrong. And if you're interested in learning more about that, me and some colleagues from Amazon, we published a paper about some of these real-world challenges that we see in the IEEE Data Engineering Bulletin last year. And I briefly want to give you two examples of research that we produced in this area of data management for machine learning that addresses some of these issues. So the first example is tailored towards what we call unit tests for data. And here the problem that we tackle is that the quality of data and the validation of data is really a crucial problem in any data intensive applications, in any use case where you make decisions based on data, but especially in machine learning applications. And data quality is very important, and it can have a lot of impact. So obviously, as soon as you make decisions based on data, then missing or incorrect data can result in wrong decision making. People also often report that if you want to improve the performance of your model, then cleaning the data is often a very easy way to improve this performance. And sometimes people observe much higher gains from cleaning the data than from running extensive model selection, for example. And the third aspect that's often overlooked is that data quality is also important for the operational stability. It's not only that your systems can give you wrong results if you feed them with wrong data, it's also that systems can crash when you feed them with wrong data. So for example, if you have missing values in your data and you use environment like the JVM, then and your code is not safe against these missing values, then you can produce null pointer exceptions because your code tries to access some data and there's nothing there, and that can lead to crashes of your applications. And the one reason why data quality is becoming a bigger and bigger problem in the last years is that data also increasingly lives outside of relational database management systems. So relational databases give you a lot of tools to manage the quality of your data. So you have a schema for your data, you can define integrity constraints and things like that. But because we want to take a data-driven approach, because it has become very cheap to store and process a lot of data, we've started to use different data stores. So we have now what's called data lakes. It's basically just folders on a distributed file system where we simply collect the data as it arrives. Data is often stored in key value stores where you don't really have a schema for the data. So you decide, okay, that's the key, and then there's some nested document that's part of that key. And also spreadsheets are still, spreadsheets and CSV files are also very, very widely used, which often have errors. And as I said, so in these cases, there's no schema that can be enforced. There's often no integrity constraints that say, I don't know, this attribute must not be null, this attribute must be unique, and things like that. And then in complex organizations, data is also very often moved between different systems. Often maybe the main data store is very difficult and very slow to access. So what people usually do is they take some small sample from that data so that they can work with the data on their local machine. But then if the data is updated in the main data store, this update is often not reflected in the copy and things like that. And in general, in real-world use cases, data sets are often combined and integrated from many heterogeneous sources, and that's a natural source of errors. So we've observed that also when I worked in industry a lot. And one inspiration that we had in tackling this problem was that we looked at what people do in software engineering. So in software engineering, it's common to write so-called unit tests for your data. That's small pieces of code that basically test other code, that invoke a method with inputs and outputs, and then simply check whether this particular piece of code gives you the correct results. And we found it odd that we have all this machinery to unit test software with continuous integration systems and things like that. But we don't have something like this for our data, and data is at least as important as code. So we wrote a paper that we published at VLDB 2 years ago, where we proposed a system that provides you with unit tests for data. That system is now open source. It's called Deequ. So it's a library for scalable data unit tests that's implemented in Apache Spark. If you want to check it out, it's available on GitHub. And it basically allows you to write something like a unit test for your data. So you basically write down in a declarative way, this is how my data should look like. And then our library takes this test and translates it into a Spark job, applies certain query optimization techniques to make sure that the resulting parallel job that tests your data can be executed efficiently. And then it scans your data and basically gives you back the results that indicate which of these checks that you described for your test held and which didn't. We designed it in a way that it can scale to terabyte-sized data sets with billions of rows and hundreds of columns if you choose the statistics to check carefully. And we also have support for use cases where you have a new piece of data every day and don't want to run the job on the whole data set, for example. This piece of work is it's widely used. So we know from users from the retail industry, from finance and health insurances, and it's also been integrated into Amazon's cloud solutions. So Amazon has a machine learning service called AWS SageMaker. And as part of that, there's the SageMaker Model Monitor service that allows you to run concept drift detection on the data that you send to your machine learning models. And that is built on top of our Deequ library. The second piece of work that's currently under submission that I want to showcase to you is about detecting technical bias in machine learning pipelines. So that's something that's aimed at increasing fairness and accountability. And so this bias in machine learning systems is a very, very complex topic, and there's very different types of bias. There could be bias in how we collect the data. There could be bias simply in the world that is reflected in our data. But there's also this what's often called technical bias, and that's basically errors in the data or that are introduced by the way in which we process the data. And it's tricky that, and the tricky thing is that we often observe is that it's easy to accidentally introduce such bias in the data when you pre-process the data for your machine learning models. So often we work with pre-made data sets that we can just import from somewhere, but usually once we have data from the real world, there is some process to integrate it, to clean it, to filter it, to convert it to features. And it's very, very easy to introduce such bias. So one example is, let's say you work with demographic data for some reason, and you just filter it by zip code. Then in many countries, the zip code or the area where someone lives is correlated with attributes or with groups that might be considered sensitive from a fairness perspective. So it could be that in certain areas, people of a certain age group live, or people of a certain race. And that means that you create an imbalance in your data set just by filtering by a column that you maybe think it's kind of innocent to do a filter by that attribute. Another case is if you have missing values in your data and you impute them, that can also lead to imbalances that you accidentally introduce in your data. Maybe for some, let's say again, you work with demographic data, and maybe for some individuals the age is missing, and then you use some kind of imputation technique that then assigns maybe all people to a certain age group. And again, this introduces imbalances. And the problem there is that at the moment, data scientists have to be aware of these issues and have to manually verify that no such problems occur in these data pipelines. And it's very, very difficult, especially in cases where maybe one person, a data engineer, creates a pipeline to fetch and process the data, and then another person just consumes the data from this pipeline and trains a model on that. Then you can have these effects. Something changes in the pipeline, the other person is not aware of that, and you get these imbalances in the model. So a solution that we developed for this is what's called mlinspect. And the idea in mlinspect is again inspired by software engineering. The idea is that we look at your code, your machine learning pipelines. In that case, we focus on Python and on data science scripts that are written using pandas and scikit-learn and some kind of library to train your models. And then we inspect this code and try to hint you at potentially problematic operations. So the inspiration here is code inspections in modern IDEs. So if you use a modern IDE like IntelliJ, for example, this will often underline some piece of code and then give you some hint. Maybe you call a deprecated method or some unsafe method that's not thread safe, or things like that. And we think that we should have the same kind of tools for machine learning. So here we look at the operations that you apply to the data, maybe join operations, filter operations that you do in pandas, or missing value imputation that's run in a scikit-learn pipeline. And from your code, we extract something like a query plan. That's this graph that you see here. And this query plan has operators that change the data, and we know some semantics of these operators, and that allows us to automatically instrument your program at runtime. So then we can, for example, compute the proportions of certain groups after a join or after filter, and then do some statistical tests to see if the distribution changed because of that operation, and we can hint you there. And we think that's a way forward for a kind of a human in the loop solution, where we have automated ways to hint you at potential problems, and then the data scientist in charge looks at these problems and can decide how severe they are or not. Okay, so that concludes the first part of this talk, the general problems in bringing machine learning to production. And now in the second part, I would like to talk about specific challenges that I see for industrial scale online recommender systems. And as I said in the beginning, I recently restarted some work on scalable recommender systems with one of our industry partners from our project here, a large European e-commerce platform. And what we're doing is we're looking at a lot of interesting algorithms from research, and we want to see which of these can be deployed in large-scale production setups. And at the moment, there's 3 big challenges that we see that we're working on, and that I would like to give you my perspective on them as part of this talk. So these 3 issues are, on the one hand, the scale of the data that you have to work with. It's kind of an evergreen issue. Then the response latency of these systems, how fast can they answer? And then a privacy-related challenge, which is to support the right to be forgotten. And let's start with scale. So I recently talked to our industry partner, and I asked them, from their perspective, what would be the minimal requirements for a scalable solution? Something where they said, okay, that's how the solution needs to perform so that they would feel comfortable to put it in production. And that's really the minimum. So they have a lot of data, and they said a scalable recommender system for them needs to work with at least 10 billion interactions. That's like where it starts. And also from a throughput perspective, the system needs to be able to answer 1,000 queries per second on average, and then there might be peak times where this system has to answer 10,000 queries every second. And also, so they have a huge catalog with a lot of items, but they said that a deployable solution should at least be able to work with 2 million distinct items so that they can deploy it. And then they have other requirements, like they need to be able to retrain the model regularly, and this retraining needs to adhere to so-called service level agreements, where basically one system guarantees to other systems that need data or models from the system that you can finish your computation in a given time. So maybe you retrain every night, and your model retraining is only allowed to take 1 hour, and then other systems need to get that model and deploy it somehow, for example. And also there's always the problem of hyperparameter optimization. So that's something that can be done offline. That's also something that can be parallelized fairly well. But a deployable solution also needs to be manageable somehow, so that it needs to have a manageable effort and a manageable cost for finding hyperparameters. And very often when I talk to people, then people might say, well, that's just engineering. So you can just sit down, have some competent engineers, and they can you give them a paper and they will build a scalable system from that. And I think that unfortunately that's not the case, simply because my observation is that it's really, really hard to build these systems, and we have a lot of competent engineers, and if it was just an engineering problem, then it would be much easier to build these systems. And I can give you some first-hand observations. So as part of a recent project that we ran with one of our industry partners, we took a very interesting study from Ludwig et al. That was published at RecSys, I think last year, where they compared different solutions for session-based recommendation. And they especially compared relatively simple nearest neighbor-based approaches to more sophisticated neural-based approaches. And in that paper, they found that performance-wise, or in terms of predictive performance, these simple baselines outperform the neural networks. And we replicated these results on our data, but we also looked at the system-specific challenges. And like one thing that we observed for one of the neural methods was that it exhibited really extremely long training times. So we ran hyperparameters optimization for one of the methods on a dedicated cloud machine with a GPU. And I think we only tested 100 combinations on 100,000 interactions, and we had to run this for 6 days in total to evaluate these hyperparameters. So that's more than an engineering problem. That's really something where there's a research problem of adapting this method. And also in research that I've done earlier, where I evaluated different nearest neighbor methods from open source libraries, I also observed that many of them cannot process even medium-sized data sets. And again, that's not to say there's something wrong with the algorithm. That's just to say that designing an algorithm and translating it into a scalable solution are two different important research problems. And I think the reason for this is that when we design algorithms, we still implicitly design them for a computer, because we are computer scientists. So in the end, everything somehow gets executed on a machine. And unfortunately, the machines nowadays and the systems are much more complicated than they used to be. So in the old days, we had one processor, and then through Moore's law, this processor got faster and faster, and your mental model was basically, well, it's one processor, has access to the data, hope that the data fits into memory, we can just randomly access. That's the way that many algorithms are designed, and that's also fine because that allows one to focus on the math and not on implementation detail. But unfortunately, Moore's law is ending now, and we have much more complicated infrastructure. So nowadays, even every phone has multiple cores, and all major companies basically use distributed systems to process the data. So parallel and distributed execution is the new normal, I would say. And that means that we cannot simply translate an abstract algorithm to code. It's not like just mapping every line of the algorithm to a line of code. We really like, I think what we have to solve is what I call the scalability puzzle. So we have to look at distributed and parallel execution and what that requires. And often that means that we have to execute the computations concurrently on some parts of the data. And also we have to partition the data. So we have to chop up the data and either put it on different machines or put it close to different cores. And we also have to be aware of the fact that for different parts of the data, we have very different access times, and that can have a very huge impact on computations. It can make a difference of some orders of magnitude. And I think that's an ongoing research area. There have been many interesting solutions, but it's not really solved. And basically, the part of this puzzle is taking an abstractly defined algorithm, taking a parallel processing system or paradigm like maybe MapReduce or Spark or parameter servers, and then figuring out how to take this algorithm and how to efficiently map it to this system so that it can be efficiently executed. I've done some of that work in the good old days when people were still using MapReduce. So there's some old papers from us where we showed how to do matrix factorization with ALS on MapReduce systems, for example. And there's a lot of work on efficient data processing with parameter servers. And I think a very interesting opportunity where I would like to see much more work here is to really design the algorithms with a certain paradigm in mind. So at SIGMOD this year, we published a paper from Amazon Research where we talked about Amazon SageMaker system, which is a streaming machine learning system, which supports common algorithms, which is very, very scalable. And for that system, people really redesigned the algorithms. So they really thought, okay, we have this scalable system that's built on top of Apache MXNet, which is a deep learning engine with a parameter server built in. And then people really redesigned the algorithms to build them in a way that they can handle streaming data and that they can work with a fixed size state. And I think that really brings you to scalable solutions that are hard to get to otherwise. So that was the first challenge. The second challenge that we ran into is response latency. So when we talk about response latency, we basically discuss the question that always arises in production setups is, how fast can my recommender system answer queries? And that's a question that's very important in production setup, but maybe not very important in academic lab conditions. So if you think about e-commerce websites, then usually these websites consist of many different internal services that are called in order to build and render the website for the users. And recommender systems are one of these services. And typically they're hard SLAs, hard service level agreements for the response latency of these systems. If they don't answer about after a certain amount of milliseconds, they will just be cut off and the website will be rendered without them. And I think this response latency is a very interesting question, especially from a systems perspective. But unfortunately, it's also a question that is very, very hard to study in academic setups. In academic setups, we often focus either on prediction quality or on the scalability of algorithms, because that's something that is easier to measure in an academic setup. We can just do offline evaluations on held out data to get a picture of the prediction quality, and then we can run some scalability experiments on our cluster to see how a solution reacts to growing data sizes, for example. But with response latency, and especially with the impact of response latency in a real-world setup, that's something that's very, very hard to measure. So we found some existing research for search engines where people basically artificially slowed down the responses of the search engine and then observed what impact it has on the acceptance. And they found a negative impact. But the catch with this research is that they can only slow down, like they can only make this response latency worse because they cannot artificially increase the response latency of the system. That's very, very difficult. But one of our industry partners ran a very interesting experiment that I would like to share with you. And they kind of ran this in a unique opportunity because they were conducting a migration from a proprietary data center that they had to the Google Cloud. And as part of this migration, they decided to optimize the response latency of many of their systems, including the serving system of their recommender system. So they rewrote some services. They updated a lot of libraries. They took special care that the systems can auto-scale themselves when there's back pressure. They even control the insertion rate when they do bulk updates into their serving system for the recommendations. So they invested a lot of work to not artificially slow down one solution, but to make one deployed system really respond much, much faster. And the interesting thing is that they also conducted an A/B test during that migration for several weeks on more than 19 million user sessions. And so this A/B test basically serves the same recommendations. So it's the same system, but deployed in two different setups, in the proprietary data center and the Google Cloud. So you get the same, you basically have the same algorithm deployed, but one of them can respond much, much faster. So they measured the P90 of the response latency of their system, basically between the front end that renders the websites and the web pages and the serving system. And they increased this P90 response latency from 32 milliseconds to 15 milliseconds. And interestingly, they observed more than a 2% increase in business relevant metrics based on orders and revenue for the faster version. So they didn't really change the algorithm. It was the same algorithm. The algorithm was just responding faster, and that gave them really a huge lift up in the metrics that they care about. And I think that's a really interesting experiment. And I think for us as academics, it's also important to think about the implications of this. So for example, as far as I know, with neural networks, you often have the problem that they respond very slow, and then there's different techniques that you can apply to increase the response latency of your model. So you can prune your model, simply remove some part of the computation, or you can reduce the precision of the computations in your model. And typically we assume, because we do offline tests, that has some kind of negative impact on the accuracy of that model, on the predictive performance. And an interesting question that what could be worthwhile to explore is the trade-off there. So you have some accuracy loss in offline tests, but maybe you have an accuracy gain or a gain in the metrics that you care about in the real world because of the increase in the latency. So that's something I wanted to share with you. And the last challenge that I want to talk about is concerned with the so-called right to be forgotten. So recently there's been different laws, especially the GDPR in Europe, that gives users a lot of control over their data, and that enforces what's often called privacy through deletion. So it basically gives users the right to request the timely deletion of their data from systems that store and process the data. And there's a lot of discussion about this, but a lot of people, including me, argue that that doesn't only apply to primary data stores like databases, but also to machine learning models that are derived from the data. And there are some cases, and we have an illustration of one case that we talked about, one constructed case that we talked about in a recent paper, where if you have the database without the deleted records and a stale machine learning model that has been trained on that data, you can do elaborated guesses about deleted data or even restore it in some cases. So if you think of recommendation models, for example, you could have a similarity matrix between users or some kind of embedding that allows you to retrieve similar users for one user who has their data deleted. And then maybe you can reconstruct this data with some certainty from these similar users, because you know they are close in the embedding space, so the original data must also be very similar to the data of that user. And from a systems perspective, from a deployment perspective, the question is also, okay, how do we now build this right to be forgotten and privacy through deletion? How do we build this into the machine learning applications and the recommender systems that we have? And at the moment, I think what's typically happening is that there's some complex bookkeeping going on. So a user requests the deletion of their data, and then that gets stored somewhere. And then once you retrain machine learning models, for example, you have to make sure that you don't use the data of these users, and then you need to redeploy the model and whatnot. So that's something that's very, very complicated. And as far as I know, in real world setups at the moment, there's still very, very long waiting times until you're guaranteed that your data is deleted from the system. So I recently looked into the documentation of the Google Cloud, which claims to be GDPR compliant, and there I think it can take, they say it can take up to 30 days until data is deleted from active systems, and up to 180 days until it's also deleted from backup systems. So I think the question is, can we do better? Can we give, if people have this right, can we give them like the technical opportunity to instantly execute this right, to instantly have their data deleted, for example? And a big problem there is that, in my opinion, in my view, a lot of the existing systems and algorithms that we have are simply not designed with data deletion in mind. So in the last years, it has become increasingly, incredibly cheap to store data. And if we look at this design, for example, of many distributed file systems, then the fine-grained deletion is not really is not really part of their design. Usually, they are designed to support very fast append-only writes, and that's really baked into the core design of these systems. So I think an interesting research challenge in that area is to think about how we can make deletes and deletion operations really first-class citizens of algorithms and systems. Our group published some preliminary work on that earlier this year at the CIDR conference in data management space. It's a conference that's usually looking for risky, innovative work. And we discussed a few approaches to efficiently delete data in place from trained machine learning models via what's often called decremental learning. So basically the opposite of incremental learning. You don't add data to your model, you try to remove data from the model. And from a deployment perspective, it would be awesome if we can do this without having to re-access the training data of the model. Because usually in these production setups, the training data, especially if it's sensitive personal data, is stored in highly secured networks, very far away and secured from the system that actually has the models deployed. So it would be great if we could find a way to just update the model in place where it is, and not have to re-execute complicated deployment pipelines. So we had some ideas, we presented some ideas on how to do that at deployment time with millisecond latency. But a limitation in this paper that I want to be honest about is also that it's only straightforward for very, very simple machine learning models, like item-based collaborative filtering, for example. But I think that's an interesting, that's also a very interesting direction for the future. And especially this angle of not requiring retraining or re-access to the training data. That's difficult, but that would make this much, much easier to deploy. And coming to the end of my talk now, and I want to try to get all these things that I talked about, to get them together and to give you an idea of basically the research that is going on now in our group, and some of these systems that we explore in order to tackle all these challenges. So I think one very, very interesting direction to explore is so-called differential computation. And that's pioneered by a system called differential data flow that Frank McSherry presented a few years ago, also at CIDR. It's built on an abstraction called timely data flow. And basically the system is a data flow system similar to Apache Spark or Apache Flink. But it's the interesting distinction is that existing data flow systems operate on collections. So in Spark, you read collections or data frames as input, you do your computations, and Spark produces new collections as output. And differential data flow doesn't directly operate on collections, it operates on differences of collections. So the input to your system are differences in the input, and the output of your system are also the differences of the outputs. Differential data flow is built on this new computational model called differential computation, which is similar to traditional incremental computation, but also allows nested iterations, which is very important for many machine learning or graph workloads. And the nice thing about that system is that there's a very efficient implementation built in Rust, and it provides a declarative data parallel data flow language. So you basically program it in a way that's similar to how you would work with collections in functional languages, or with systems like Spark or Flink, where you have these data flow operations that you can chain together, like joins, filters, maps, reduces, and things like that. And also differential data flow is publicly available, it's open source. So at the moment we're looking on differential data flow and playing with different implementations of recommendation algorithms on top of it. And we think that it's very well suited to tackling these problems that I outlined. So for the problem of scale, I think that is covered because data parallel execution with a data flow model that can be efficiently parallelized across different cores and also across different computers is, in my view, a proven paradigm. So Spark and Flink are built on top of this paradigm, and both of them have been very successful and are widely used in many real-world deployments. I think differential data flow is also very much geared to providing low latency responses, because in general, if you have a computational model and a system that's really built for just computing the differences of outputs, that's something that has a natural synergy with low response latencies, because you really try to avoid to redo computations as much as possible. And in my view, the most interesting thing and also the most distinguishing fact is that differential data flow has delete operations built in as a first-class citizen. So if you read the papers or the documentation of the system about their computational model, then really deleting data, basically one difference. So a difference is either you add something to an input collection or you remove something from an input collection. So it's really something that's built into the abstract foundational model on which the system is implemented. So and I think that that for example immediately gives you things like joins or even more complicated data flows that allow you to remove data and that will recompute what changes once you remove this data. So I think that's something very nice to play around with, and that doesn't require us to do the foundational work. If you're interested in learning more about that, we have an example implementation of a simple but classic item-based collaborative filtering that we contributed to differential data flow. And at the moment, we're basically investigating implementations of more recent algorithms on top of this system. And with that, I'm closing the talk. I hope that I could give you some interesting insights or new directions or problems to work on. In summary, I tried to convince you that bridging the gap between machine learning research and machine learning production is a hard problem. It's also a hard research problem. The route that I think needs to be taken is to adapt and reinvent many of the existing techniques from data management and software engineering. And there are these three challenges that I see for industrial scale recommender systems: scale, response latency, and supporting efficient data forgetting. And I think that differential computation is one of the interesting directions that we should look into. And with that, I close the keynote, and I'm happy to answer questions if you have some. Thank you very much.
I think that's a very, very interesting question. So I guess I might have two answers for you. So one thing that I've often seen is that in deploying models, it's kind of a process. So you want to start with a very simple model, have that as a baseline, and then you want to do incremental improvements. And very often you want to do get something deployed very fast that, I don't know, gets the problem 80% of the time right, and then you basically iterate on more complex solutions or more niche solutions for some parts of the data to get the rest done. So that's one thing. And so Google has a very interesting book. I think it's called Rules for Machine Learning Engineering, where they basically talk about the empirical process that they found to work well for starting, deploying, and developing machine learning applications. And they talk about this, like you start with a very simple solution, and then over time they describe how they come up with more complex models. And then I think in the end, it's often also an economic question of how much a company wants to invest and how much they gain from a more expensive model. So I think in many cases, maybe if you're a small online shop, then a very simple, easy model is fine for you, and you don't want to pay a lot of cost for deploying and maintaining this model. But if you're the Google Ads team, then I mean Google is basically building their own supercomputers to train their models and improve their machine learning systems. So for them, all this complexity is paying off. So I think there's these two dimensions.
Right, that makes sense. Thank you.
Okay, anyone else would like to make a question?
Oh, I have a question. Thanks a lot for the great talk. Again, I'm just trying to follow up on the previous question. So if you take machine learning models, I mean, for a simple, let's say, collaborative filtering kind of problem, there are tons of models out there, like, starting from simplistic models to more complex ones. So how much exploration do you think is feasible, in implementing all these models? Are you going to, like, I don't know, explore 100 papers and then implement all of them, or you just, how do you select and narrow down things?
That's a very good question. So I think, or at least for what I've seen, there is some tribal knowledge. Like people in industry often talk about what works well, and I think usually you also want to have some kind of cheap process to try a lot of models and then see how kind of judge their potential. So I've mentioned this in the talk. A few years ago, I interned with the recommender systems team at Twitter, and they had kind of an interesting process. So whenever they had an idea or someone came across an interesting paper, they would first try it out on let's say on the Twitter accounts of themselves and of the team to see if things made sense, if they looked interesting. And then if that made sense, they did a more thorough offline evaluation. And then if that still looked well, they spent some time implementing a small A/B test. And again, if that looked well, they basically try to get investment for building a real scalable system to roll this out at a larger scale. And I think the interesting or the challenge is that you need to have some kind of process in place for judging the potential of ideas, and then ideally you probably want to test as many ideas or papers as possible.
Thank you.
Okay, we're a little bit behind schedule, so maybe we should go on. Once again, Sebastian, thank you for your very interesting talk.
Yeah, thanks for having me.
Okay, it was great. So I think we can interact somehow during the conference on Wova, and anyone would like to ask you questions. I assume that you will be available.
Yeah, I'm
sometime.
available.
Okay.
I'm also active on Twitter, so you can also just tweet at me.
So that's great. So the round of applause isn't very loud, but I guess everyone is clapping. So without further ado, I would pass to the first paper of the workshop, which has the title User Modeling and Churn Prediction in Over-the-Top Media Services. And this paper will be presented by Vineet Rakesh. Okay, go ahead.
Thank you. So shall I just share my screen?
Yes, of course.
Yeah, okay.
You should be able to.
Let me see. Sorry. Sorry, got disconnected. It says like I cannot share the screen because the host has disabled it.
So let me just. So you should be able to share now.
Thank you. Yeah. Hi everyone. Thanks for tuning in. So our paper is on user modeling and churn prediction in over-the-top media services. So we address the problem of customer retention, which is churn, in over-the-top streaming devices. These are your typical streaming devices such as Apple TV, Roku, and Amazon Fire TV, and so on. In the first part of our paper, what we do is we do some form of behavioral analysis to understand how people interact with apps and how consistently they interact with their OTT boxes. And what happens to dormant users? Do they stay dormant or do they come alive after a certain period of time, and so on? And we do a lot of feature engineering in this phase. In the second part, we propose two different models to basically predict churn. So the reasons for churn could be very different, and we have a plethora of features. And we categorize the features into two different kinds. One is the application specific, and the other one is the device specific. Application level specific features are attributed by the apps themselves. For instance, it could be because of the lack of compelling content provided by an app, or people might have an affinity to a different app because maybe the app crashes quite frequently, it's not optimized, and so on. Or the content provided by the app could be very long. For instance, some apps could just provide movies as a service, and people might have limited budget. So there are several reasons for this. And the second group is the device-specific reasons, and these typically include reboots, poor Wi-Fi connections, and high memory usage, and so on. So let's take a look at some of the naive approaches that we can adopt to predict churn. First, what we can do is we can fix an observation time window T, and we extract a certain bunch of features, and then we can apply some form of suitable classification model to predict the churn after that specific time period T. Now, the problems with this naive approach is that we have a very high dimensional data, and we're looking at several time windows. So it quickly becomes impractical to implement. The other problem is by flattening the features, you're losing out on temporal correlation. Now, obviously, a good choice for such a setup is a time series model, such as recurrent neural networks, which have shown extremely promising results, especially in NLP domain and in other domains recently. One problem in directly applying the vanilla RNN is that when you get the latent vector representation, this compressed representation usually doesn't capture a long temporal, like the qualities in a long temporal sequence. And this is a widely known aspect of recurrent neural networks, especially in the natural language processing domain. And the second problem is difficulty to interpret results. And typically, deep learning models being mostly black box models, it's very difficult to understand the results that's outputted by the models. Unfortunately, due to privacy reasons, I cannot disclose the actual data set, but we're working to anonymize data set, and hopefully we might be able to get a toy data set out there. But our research was done on several, like 31K OTT devices that we obtained from a very large service provider. And the data spans from September 2018 to April 2019. We pre-processed the data in several different ways, and you can take a look at our paper to understand the pre-processing steps. Basically, we divide the data into two different parts. A data set we call D, which includes all the apps, including default apps. In our case, the default apps are the ones that comes with the OTT box, such as apps include Netflix, Sling, etc. And DE is another data set where we exclude the default apps. And the reasons for doing this is because of two reasons. First, for churn prediction, we need the actual start date of an app. Like, we need to know when a user starts using an app. And unfortunately, we cannot get this for the default apps. The second reason is the popularity bias. And what we found is that most of the people tend to use the default apps that come with the boxes. We further divide this data set D and D into multiple time frames, because our objective is to detect the churn as soon as possible. So for instance, in this example, if D is equal to 5 implies we only use features within 5 days. It could be continuous or it could be discontinuous. I'm not going to describe all the user characteristics, and for details, you can look at the paper. The most interesting thing we found and we use for churn prediction is the inter-arrival time between the apps. So for every app, we calculate, let's say a user uses an app A, and we calculate how long does he relaunches the app and how much time he takes. It could be a few days or it could be a few hours and so on. So, and we take the maximum and we plot it in this figure D. What we found is that a user, if he doesn't churn, he usually tends to come back within a maximum of 6 days. So the other problem we faced was to label churners. Labeling is very difficult task because we don't have explicit signal as to when a person churns. So to overcome this issue, we used the inactivity threshold, which is the inter-arrival time between the apps, and we set that as 10 days, meaning if a person doesn't use an app for 10 days, he most likely churns. And the second threshold we set was the engagement threshold. A lot of people usually tend to download an app just because it seems interesting and never use them. We don't consider such users. We want to make sure that the user has genuinely tried an app for at least 3 sessions, and we only consider such user app combination. Again, I'm showing just a small piece of the statistical analysis. So this is some of the plots from people who exclusively churn. So figure A shows that people who download more apps tend to churn more, which is pretty obvious. And the one to the right, figure B, is more interesting in the sense that we find people who churn tend to switch frequently between the apps. And the frequency of switching is measured using average session switching, which is displayed on the y-axis. Finally, we wanted to see what patterns emerge from our data sets. To do this, we basically compute the cumulative distribution of how much a user engages with his or her OTT box. And then we basically fit a nonlinear function and learn the slope, intercept, and standard error. And we use these as features to a k-means clustering, and basically manually observe the patterns from the clusters, and the cluster size is set using a silhouette coefficient. What we found is that we basically find 4 major types of users. From clockwise, from the left corner, we have mid-bloomers who basically remain dormant for a while and then start using the OTT box extensively during the mid phase. The second type of users are the late bloomers. And the third one we call as potential churners, where we think these are the users we are interested in or targeting, because they use the OTT box a lot at the first phase, and then for some reason they kind of stop using it. And this is indicated by a very low standard deviation. And finally, you have the consistent users who constantly tend to use the OTT box from the start to the end of the trial period. So these are the proposed models. To the left is the ALSTM, or a simple attention LSTM. This is an extension of the neural language translation model, and this is just a extension for churn prediction. So where we have attention for each time frame, we basically give all the features. Some features are temporal, some features are not. We have about 12 different features, which also includes the engineered set of features. And for each time frame, we have an attention, and we predict the churn using a simple feed-forward neural network. To the right is the proposed NCPM, which is the neural churn prediction model, where we have individual ALSTMs which captures every single feature. So every single feature gets this exclusive ALSTM, and we apply another second layer of attention, which is the attention block B in this figure, where we put weights on different features, and then we finally get the weighted vector representation, and then predict the churn. These are some of the results. Again, for details, please take a look at our paper. We perform really good on several different settings, both for non-default apps and all apps, and both for continuous and non-continuous data sets. We compare our model against simple logistic regression, random forest, which surprisingly does perform well, and another variation of multi-layer perceptron, and ALSTM, and the NCPM, which is the main proposed model. Yes, we do perform well, but then one of the biggest things biggest problems in ML is interpretability. So we can achieve some form of interpretability in our setting, in the sense we can, in this example, you can see from figures A and C that if you just include the first 10 days of data for a user, it weighs more on the cluster, the type of cluster, that is the user type, and the number of downloads. But as we incorporate more and more data, it looks like the attention weights are shifted to some, for instance, for the non-default app, it is weighing more on the inter-arrival time, whereas for the default apps, it is weighing more on the number of reboots. Again, this is a much in-depth look at how attentions are applied on each, like the individual type of users that I explained earlier, where MB is the mid-bloomers, LB is the late bloomers, PC is the potential churners, which we hypothesized as they're probably likely to churn, and CU is the consistent users. This clearly supports our hypothesis, where you can see from figure A that there's a very high attention score for potential churners to churn when compared to consistent users. To the right is the same graph, but this is the attention is done for different elapsed time duration. For instance, when you take a look at 10 to 20% of elapsed time duration, you can see that the attentions on all 4 types of users are very less. This is mainly because we do not have enough data available about them. And as we move on, you can see a very high weight given to all types of users, especially on potential churners. And towards the end, around 80 to 100% of the elapsed duration, the attention weights go down because you have signals from several other features. With that, I conclude my talk. If you have any questions, I would be happy to answer. Thank you.
Thank you. Any questions? You can turn on the microphone and the camera if you wish to ask questions, everyone.
Hi.
Oh,
Can you
hello.
hear me?
Yeah.
Thanks for the interesting paper. I have a question. Did you set a minimum amount of time to define a session?
Yes, so we did define, though that is a part of the pre-processing step. So for instance, we eliminate all the sessions that are less than a minute or so. So we did set a threshold, but on the top of my head, I don't remember the exact number, but yeah, we definitely eliminated all the sessions that are less than a minute.
Okay, thank you.
Anyone else?
Anyone?
Just out of curiosity, do you have any clue for how random forests perform so well among all the sophisticated stuff?
Yeah, I mean, I do constantly find random forests. I mean, we have several different data sets, not only on this data set, or on several. I mean, it depends. It looks like, at least we have a lot of noise in this data set. So it's quite possible that within that short duration, let's say whatever information we had did not have a very strong temporal signal. So random forest still performs so well. And the other important thing is that the people are limited to like 5 or 10 apps. I mean, most of them use like 3 or 4 apps and not beyond that. So the temporal signal sometimes does not make a lot of sense. So that's mainly one of the reasons why random forest still tends to perform well. That's yeah.
Okay, thanks. So I guess we'll move on to the next paper. So thanks again, Vineeth. A round of applause, a virtual applause. So the next paper is CPR, Collaborative Pairwise Ranking for Online Lists Recommendations. The presenter is Saurabh Gupta. I hope I pronounced it reasonably well. So
yeah, that's right.
Go ahead.
All right. Hello, everyone. My name is Saurabh, and I'm an applied scientist at Amazon. And today I'll be presenting our work on CPR, which is Collaborative Pairwise Ranking for Online List Recommendations. And this work was done in collaboration with my colleagues from Amazon, Bharat and Anna. So let me start by giving you an overview of how does an online top K recommender system look like. So let's assume that we already have a model or an agent that can make recommendations by taking in users and items features. So a user arrives at our website or our app. We can define the user from either the observable features or the latent features that we might have learned from this user's past interactions. And then we have a big catalog of items from which we generate a candidate list. And then we pass the features of these items to this model. The model recommends a list of items. The user interacts with this list. We log feedback that is given by user. It can be both implicit and explicit. And then finally, we retrain the model. So the key idea here is the interactive nature of the system. We need to be able to update the model as soon as possible so as to deliver a very good user experience. Now, such a system has several challenges, and let's look at a typical pipeline of an interactive model. So let's say we start from scratch. So we just have some user interactions from which we can learn a model. Let's say a collaborative filtering matrix factorization based model. We train that over the period of time. We have new users and items coming in. We log more interactions, and then we again retrain the model. So again, the challenges with the system are first related to retraining of model. So, sorry. Yeah. So first we need to answer, like, how soon we should retrain the model, with what amount of data we should use for retraining. And then there are some questions related to the exploration and exploitation trade-off, which means whether we should exploit whatever we know about the current user, or we should like explore more about the user preferences by recommending, let's say, a diverse set of items. This trade-off also arises because of something called partial feedback. So essentially we get feedback only for the items that we recommend, unless the user actually explicitly goes and searches for the items he or she is interested in. But because of this partial feedback, it becomes really important to explore and exploit in a well-balanced way. Again, for new users and items, it might be possible that we know nothing about them. So we need to deliver a very good experience, and we need to be very careful with what items we recommend to the user, especially new users. And in most of the cases, just recommending one item is not enough. While most of the algorithms are designed for just recommending top one item, like in our work, we'll later on present a generalized algorithm that can actually present a list of items. A list recommendations is especially challenging because it's actually hard to see how the user gives feedback by traversing over that list. So we'll see the complications about the list recommendation part in a moment. So we first start exploring contextual bandits because they offer a very good mathematical framework that fits into the problem that I just talked about. So contextual bandits, basically the agent interacts with an environment, the agent takes a state from the environment and takes an action A. And depending on this action, the agent gets a reward, and accordingly it updates its weights. So the state here from the context of, let's say, movie recommendation can be either user features or movie features, or there can be some common features or some common context like, time, device, location, etc. So under the hood, contextual bandits actually maintain a reward estimate, or which is also known as a Q value. And this Q value depends on the state and the action. So contextual bandits usually have two main aspects. So one is the base predictor. In most of the cases, it's online linear regression. So it's a very simple model where, phi of S and A are the feature vectors and theta R is the weight of the model that is actually learned. Or we can also have like more complex predictors like decision trees, neural networks, and so on. In terms of exploration strategies, so these are the strategies that actually decide which action to take, how to handle or balance the exploration exploitation trade-off. So amongst these, epsilon greedy is pretty straightforward, where the agent decides to, let's say, 10% of the time it will just explore randomly. It will recommend random items, whereas 90% of the times it will take the best action according to this scoring function or Q value. Lin UCB and Lin TS are like more complex strategies where they try to maintain an uncertainty estimate of the reward that they know for a particular action. And based on that uncertainty estimate, they decide how to explore or how to exploit. So UCB actually stands for upper confidence bound. It basically operates on the principle of optimism in the face of uncertainty. So whenever it's uncertain about certain actions, it tries to be as optimistic as it can. And LinTS is linear Thompson sampling. So what it does is it actually maintains a posterior distribution over the weights. And whenever it has to make a decision, it actually samples the weights from the posterior, makes a decision according to this scoring function again, and then updates this posterior distribution accordingly based on the reward it gets. So those were, so Lin UCB and Lin TS are algorithms that we use as baselines for our interactive recommender system problem. Another interesting bandits algorithm is HLin UCB, which actually stands for hidden. So essentially what it does is, you can think of it as online matrix factorization. So in addition to learning just the weights of the model, it actually learns the latent feature representations of both the users and items. And in addition, it can also take as input the observable features of both users and items. So in this case, the weights of the model are actually the latent item feature, the latent user feature. And the exploration part is actually handled by the UCB algorithm itself. So for more mathematical details, please feel free to have a look at this paper. So one problem with all the bandits algorithms that I've described is one item recommendation. So by default, all these algorithms just recommend one item, which mostly does not suffice in practical use cases. So what we do is we present a very simple extension to ranking, and how we do that. So we just score all the items and return the items with top case scores. That's how we do list recommendations. But then how do we incorporate the feedback? So for that, we have to make some assumptions on how the user actually scans the list of items. So we assume something called a cascading click model, where the user actually scans the list from left to right in the horizontal slate case. And for the items that the user skips, we assume that the user is not interested in them. We give them a reward of 0. And for the item that the user actually clicks on, we give it a reward of 1. And we assume that the user stops here according to some probability. And for the items that are basically after the item that the user clicked on, we actually don't give any feedback, because we are unsure whether the user actually looked at that item or not. And for all these extensions, we call them Cascadelin TS, Cascadelin UCB, and KHLin UCB. So before I dive deeper into our proposed algorithm, let me quickly talk about another online learning to rank algorithm, which is called PDGD. PDGD stands for Pairwise Differentiable Gradient Descent. So this algorithm, what it does is it actually constructs a weighted differentiable pairwise loss after each interaction. So essentially what it's trying to do is based on the user interaction, let's say user clicked on item 3 and did not click on item 2. So it'll construct a probability where we say that item 3 is preferred over item 2, which is given by this formula, where PDI is just the probability of recommending item DI, and the PDJ is just the probability of recommending item DJ. And the algorithm tries to maximize this probability directly by constructing a gradient function from it. So I'll leave the math details, but intuitively, it directly optimizes based on the inferred preferences that it gets from the user behavior. So in our paper, we actually propose an algorithm called collaborative pairwise ranking, which is an extension of the PDGD algorithm, which I described briefly here. So PDGD has some limitations as to, in order to make a recommendation, it needs to get feature representations of the respective documents, and there's no collaborative learning across users. So we try to fulfill these shortcomings by proposing a modified form of PDGD, where we are actually learning a scoring function that learns the latent features of users and items. So it's very much like online matrix factorization, but with a different loss function, where we actually directly try to optimize the item preferences that we see in user behavior. And this algorithm also has certain advantages over the bandit approaches that I described earlier. So in this approach, we are using a pairwise ranking loss instead of a regression target, which is actually more effective. And our scoring function f theta gamma can be any differentiable model, including neural networks. In the experiments that I'm going to describe, we just used a very simple linear function, which is actually a dot product of the latent features, but we can have more complex models. There's an implicit explore-exploit mechanism that comes out from the Plackett-Lewis distribution. And compared to bandits, it has like much less parameters, because bandit algorithms usually need to maintain a covariance matrix for the user weights usually, but this algorithm just needs to maintain theta and gamma, which are the latent features of the users and items. So before I dive into the results, let me quickly show you how we simulate an online or interactive recommendation environment using the MovieLens dataset. So we all know the MovieLens dataset is pretty straightforward. It looks like this. So we have users, movies, and the ratings. So we start from scratch. We assume that we don't know anything about the users or the movies. We don't know anything about their latent features. At every time step, we pick a user randomly, and we generate some candidate movies. So for simplicity, we just like take movies that have these ratings by the corresponding user in the actual dataset, because we don't want to make like any approximations here. We could, of course, like do matrix factorization on the movie lens dataset itself, and then our candidates can be the whole set of movies. But yeah, just for the sake of simplicity, we just choose the movies that the particular user has rated in the dataset. And then to compute the reward, we actually rely on a user choice model, about which I'll just describe in the next slide. So the workflow looks like this. Once we have a user and the corresponding movie IDs, we send that to our agent, whether it's bandits or it's the CPR algorithm, which I just described. This algorithm or agent recommends a list of movies. And then we use this list of movies along with the user choice model and the ratings, the ground truth ratings, to compute rewards. Please note that we are not exposing these ground truth ratings to the agent directly. We are exposing them to the agent through a reward, which we compute using a user choice model. So this is how the workflow looks like. And now let me describe what the user choice model is. So we have three different types of users here. So perfect, navigational, and informational. So perfect user is one. So let's actually pick the example of a perfect user. So here we have described the click probabilities corresponding to the ground truth ratings. And here we have the stop probabilities corresponding to the ground truth ratings. So a perfect user, what does that mean is if the user is presented with a list of items like this, let's say user has rated 1 star to items 1 and 2 and 5 stars to item 3, then the user will actually skip the first 2 items because the rating is 1 and the click probability is 0. And the user will actually click on the third item because the rating is 5 and the click probability is 1. And the user will stop after that because for the perfect user, we have like stop probability is basically 1 for a rating of 5. So that's for the perfect user. But to emulate like more, to emulate noisier environments, we have navigational and informational users here. And as you can see, the probability for them varies. And with these users, we incorporate like more noise into the user behavior. Yeah. So let's have a quick look at the results. So on the y-axis, we have cumulative NDCG here, which is a ranking metric. And on the x-axis, we have impressions or time. And then we have results for 3 different types of users that I just described. So informational user is the noisiest of all. And perfect user, as the name suggests, is the least noisy. And for all the baselines, I have the banded baseline. So for k-echelon UCB, I have 2 different versions here. So k-echelon UCB in orange is the standard echelon UCB algorithm, whereas echelon UCB greedy is the one where we have actually disabled exploration, and the algorithm like is greedy and always does the exploitation. So in the perfect environment, we see that our proposed algorithm CPR performs the best, followed by echelon UCB greedy. And the reason for that is that because of less noise, it does not make a lot of sense to explore. Exploration might hurt in some of the cases. So so the conclusion is that it's best to be greedy here. And then that's followed by Cascadillion UCB, Cascadillion TS, and finally we have random. Similarly for navigational, we actually see that the Cascadillion UCB, the orange one, actually starts performing better because with more noise, we need to do more exploration, and CPR still performs the best. One thing I want to talk about is the NCF here. It's actually almost the worst of all. NCF stands for Neural Collaborative Filtering. So it's actually a very good algorithm, but the problem is that in this particular use case, it's really hard to train this algorithm in an online fashion. There are a variety of reasons for it. Hyperparameter tuning is really hard for neural networks, especially things like batch size, learning rate, because neural networks face this issue of catastrophic forgetting. So it's really hard to tune the learning rate. And it's also hard to decide at what frequency we should update the network. So all other algorithms are updated with every user interaction, whereas for neural networks, it's really computationally intensive to update them with every interaction. So we choose to update them after every 100 interactions or so. But yeah, at a high level, these are the results and different performances of different algorithms. So that's mostly it. And we still have some open research questions that we want to answer in the future. So we need to actually test our algorithm with neural nets. we need to see how the algorithm adapts to changing user preferences, which is actually pretty common in practical scenarios. We also want to try out different click modeling solutions. Right now, we tested with the cascading solution, which is kind of a strict assumption, but we want to try out more realistic click models. Yeah, so that's mostly it, and I'll be happy to answer any questions.
Okay, thank you. So we're basically 15 minutes past the end of the session, but it's not your fault, of course. But I guess we can answer. You can ask questions. A couple of questions. We have time for that, and because the beginning of the next session is only 45 minutes from now, so you're welcome to ask any questions.
I have a question. I need you. Can you hear me?
Yeah, please go ahead.
Oh yeah, thanks a lot for the great talk. So, so you were mentioning the catastrophic forgetting. So obviously this is a lot of more problem in neural networks, but that being said, this is also a problem in any general ML models. So I was just wondering if, like, how is your setup? Do you retrain your model from scratch when you get a new exploration and new data points? Do you train your model from scratch, or do you just use the new data points and then retrain your models? And did you compare like how catastrophically it forgets, a neural network forgets versus the model that you proposed?
Yeah, so our model is actually pretty simple. It's just a variant of online linear regression, I would say. And online linear regression, the updates have a very good closed form. So, and again, for all of the bandits algorithm, since these are also doing online linear regression at the backend. So again, they have very good closed form updates. You can update the model with just one new data point. For neural networks, yes, that's catastrophic forgetting is a very big problem. And there are certain techniques to avoid that. So what we do is, which I did not mention, is we also maintain an experience replay buffer. So basically what we are doing is, just like in reinforcement learning, we have a replay buffer. We are maintaining a buffer of all the interactions. And every time we update the network, we actually sample a batch from the buffer. So we are not necessarily just looking at the latest data points. But whenever we are doing the updates, we are also like sampling some old data points. Now, to decide the level of catastrophic forgetting, it depends a lot on how big the circular buffer is. So it totally depends on the context of your problem. So if you have like user preferences that change a lot over time, then you want this circular buffer to be much smaller. But if you have a very static environment, then you want this buffer to be almost infinite and keep track of like all the old historic interactions as well.
I see. So, so when you say circular buffer, so is it, so you only take like a part of a old data set and you merge it with the newly explored data set and retrain it?
Exactly. So let's say the size of buffer is 1,000. So we just store the last 1,000 interactions. Yeah. And then we can vary the size depending on the context. Yeah.
Thank you.
We can have another question if you wish. So I guess there are no other questions. Yeah. So a round of a virtual applause.
Thank you.
Thank you for your presentation, and sorry for the small delay here. Okay. So we will be back in about 40 minutes. So you're all welcome. If you want to stick around, you can stick around. There's no problem. And see you soon. Hi, everyone. Welcome back. So this is the second session for our workshop, Awesome 2020. So in this session, we have 6 paper presentations, 3 long papers and 3 short papers interleaved. So the first paper is, just a minute. The first paper is deploying a cost-effective and production-ready deep news recommender system in the media crisis context. The presenter is Jean-Philippe Corbeil. I hope I didn't mispronounce your name. Jean-Philippe is around, but the presentation is recorded because of bandwidth problems. So I'll just put the presentation on, and then in the end, Jean-Philippe can answer questions. Okay, just give me a minute here. Sorry, the video computer is not responding. I'll just try to put the video in this one.
Welcome everyone. I hope you had a good dinner. I'm Jean-Philippe Corbeil. I'm a developer at Le Devoir. And today I'm going to present you a case study on deploying a cost-effective and production-ready deep news recommender system during the media crisis. So today we're going to follow this plan. So let's begin. In the last couple of decades, we've seen the readers changing their ways of consuming news from paper to applications. Today, we can read the news basically on our phone and get notifications at any time of the day. We have seen, among other things, social networks getting in the middle of the reader and the publishers. Online medias have now difficulties keeping their users on their platform, and one solution that we have to be able to keep users on the platform is personalization. At Le Devoir, a French-Canadian independent journal, we consider building a recommender system as a part of the solution to keep users on a platform. Yet, when we looked at current solutions like those available with Google or Element AI, and they are quite expensive for small or medium publishers or online medias like we are. So we need an optimized system that can be at the same time cost-effective and production-ready to serve all our high traffic. First, we have to keep reasonable training time so that it's not that long to train a model. Then we also have to have a good inference time so that it's not long to serve people and that we can serve them in time. The second consideration is the scalability of the model and the overall infrastructure. If there's a big breaking news, we need to be able to adapt to this kind of traffic instantly. And after that, we need to have recommender system that is reasonable in costs. Our contributions today are the case study about our deployment. We also have a contribution about the design of our news recommender system for short-time recommendations. We also have our dashboard for our news recommender system. We also release an anonymized data set. Finally, we have good offline performances, and we also present 2 qualitative experiments. So for the background, we first can find a case study which is presenting the RecSys system by Garcin et al. A review of the news recommender system domain. We have Karemi et al. In 2018 that present their suggestions about the domain. And their first remark was about the issue that we see with systems proposed in the literature that are not scalable enough. Second, they also noted that in the news domain, we see that there's a huge consideration about how can we dynamically address the addition of publication throughout the day. Online media publish a lot of articles per day, so we have to be able to recommend them in real time. So they propose that most systems consider having an efficient short-term predictions engine and then having a sophisticated. We also have another review by Zhang et al. In 2019 that mentions that the sequential nature of the news recommendation requires deep architectures. For our methodology, we first divided the problem in 2 parts. We have the analytic part and the recommender system part. So for the analytic part, we have how the reader come to our website and then how we track him with Matomo database. Most online media will use Google Analytics or Firebase. For us, Matomo was the best choice because we can get access to all our data and it's open source and free. And then from this, we have to consider the problem that GPUs are quite expensive when we design the recommender system over that. So for the recommender system, we went with the design in 2 virtual machine VM. So first, at the bottom, we have 1 virtual machine that is responsible for serving the reader in recommendation. And also to keep track of all the system states. With that, we also have a training VM, which is responsible for training the model when we ask him to train one. So when this model is trained, we can drop it into the GCP bucket on the Google Cloud platform, and then with the serving VM can get back the model and serve it in real time. We also have a MongoDB database in which we record the state of the training VM, the serving VM, and with that we can see on the dashboard what's going on. So if we look at all the system, we see that the reader comes to our website, we track him, then with the serving VM we can identify which user it is, which articles he has seen in the last couple of articles he looked at, and then we can serve him recommendation based on that. So we see here the training VM that can close automatically when it's done doing its training so that it doesn't cost us any more. So to manage both the training VM and the serving VM image, we have this old CI/CD pipeline. Both projects are hosted on a GitHub repository, of which the master branch is automatically triggering the Circle CI platform to test the code and build the Docker image when pushing this image on the GCR Google Container Registry when it's ready, and then deploying it in the Kubernetes cluster of Google. So from this, we built a data set that we released with this paper. This data set is made up of reader and article interactions with the timestamp. It's a data set with about 2 million data points from May 7th, 2020 to May 11th, 2020. We did the train test split of 90% and 10% based on the user, which means that the user that we have in the train set are not the user that we have in the test set. Then our training set have about 215 samples, and our test set have about 22,000 samples. We released this data set on our GitHub. So if we want to look a bit at how data looks like, we have user at the bottom and we have articles at the top. So first, we have a first interaction between our users and the articles. And for instance, we see that the green user have read the purple article. And then at the second timestamp, we see that the green and the gray user have both read the red articles. So we keep all these interactions and how they happen in a timely fashion. So to build our model, we use the Spotlight library. They have sequential deep models. We have the CNN model available, the LSTM, the pooling, and the mixture LSTM available. So inside this library, we have all these algorithms. We fixed a couple of hyperparameters from them, both based on our pre-experimentation and based on also the recommendation of the library. So we have the number of epochs that we fixed at 10. We have the learning rate that we fixed at 1e-2. We have the random state at 42. We have taken sequences from 3 to 7 articles when we parse them into sequences of articles. And we recommend at the output of the model 5 articles. So to find the best configuration for our models, we went with a grid search approach. We tested batch size of 512, 1024, 2048, 4096, and 8192. For the embedding size, we tested the 32 and 64 dimensions. And for the negative samples, we tested the 100, 200, and 300 settings. So when we will be done with the recommender system, we want it to look like this. At the right, we have our recommendation box with the purple headlines, which is vos recommandations, which means your recommendations. We have 5 articles, and that are those that we want to recommend. So to keep track of all this, we also built a dashboard using the dash from Plotly. So regarding the qualitative test, we have the quality embedding test. So for this, we use 5 sections of our website. It's the economy, the politics, the world, the opinion, the culture. We use the embeddings for the articles from those sections. We reduce the dimension to 3 dimensions with the Disney algorithm. And then we can try to look at this space and distinguish clusters and see if there's relation with the sections of the website. If we see good enough clusters, it means that we have high quality embedding. Also, we have a second test, the fake user recommendation test. So we again took these 5 sections, and then for each section we created a fake user which chose randomly 2 articles for each sections, and then we analyzed the recommendations for each of those fake user. So as for the results, if we look first at the results of the models, what we observe is that the best model is a CNN settings with 32 embedding dimension, 2048 batch size, a negative sampling of 300s, and it got performances of 0.693 MRR and also a PS5 of 0.133. We can train such model in 134 seconds. From this, we also see below it LSTM networks, which are performing closely, but are longer to train. We have other CNNs, and we also have a mixture LSTM, but it takes a lot of time to train such networks, so we didn't consider such approach. We can also see that the negative samplings for all the best configurations is always 300 samples, so we need to take a lot of negative samples to get a good model in the end. And also the batch size is always in the smaller part of the space that we search for. So for the embedding quality tests, we observe for the May 20th, 2020, and also for May 26th, 2020, and that in both cases we observe clusters for all 5 sections that we mentioned before. So this was a pretty good observations that we have seen there, and we can also move it around in 3D into the dashboard. So that was also very good. And for the fake user recommendation test, we have this interface in which we can input the articles and also choose sections from which to choose articles. And then when we submit it, we observe the recommendations from the model at the bottom. When we input, in this example, the politic section articles, we observe that 3 on 5 were also politics articles, and since both articles are also related to COVID-19 articles, we also observe such topics in the articles recommended. So if we look at the results for all 5, we see that in most cases we have between 2 and 3 articles that are in the same sections, which is quite good. And for the rest, we have other related topics such as society. We also have related topics like when we input Trump articles, we see Trump recommendations, and also for TV shows we see. And also for TV shows we see the same pattern. After that, we did a traffic benchmark, and we just to see how much time it took to get a recommendation, and we observe on average 3 seconds of delay, which is okay in our case since we display the box of recommendations dynamically and asynchronously. So for the cost, if we look at our solution right now, based on the Google price calculator, the solution from Google, as proposed on their website, it's about $200 a day to get recommendations out. This is really not a good solution for small, medium publishers. If we go straight ahead with our solution, but no split of the virtual machine, only one machine with a GPU, observe that we get $20 US a day, which is again a lot for small publishers. But then if we go on with our actual architectures with dynamical training across the day, we see that we get $4 a day, which is very good. So then for the limitations about our current architecture, we know that the metrics that we use to quantify the performance of the model are not the best. We want to extract the rating time of articles to compute the NDCG at 5. But it will be done in the future. We also have done a small grid search approach. We might need to do a larger one to get better results, but for now, the performance that we've seen are very good for what we want to do. We also know that our qualitative tests are not generalizable, but they give a good insights of how the model will perform with real user and real readers. So, and we also look at the results in different time period, and it gave similar results. So we are pretty confident that our setup is very good. As of the future works, we want to also integrate a content-based approach to consider the long-term recommendations. We didn't address the cold start issue directly. We also want to further optimize the pipeline to get shorter inference time. So to conclude, we present a case study on deployment of a short news recommender system. We present its architecture, and it follows the deep sequential model proposed by Zhang et al. It also has many quick trainings, which was recommended by Karimi et al. A model that is trained from scratch following the continuous integration and continuous delivery principle. This leads to scalability and flexibility of the model and the architecture. Overall, all this is very cost effective. In the end, we have also a dashboard to follow all that. In this study, we also presented qualitative tests to get insights from the model and how it behaves. From the embedding space and the fake user test, we see that our model is good, and the offline performance are also quite good. So finally, if you want to see our data that is anonymized. It's released on GitHub. You can go and look for Le Devoir and you will find the data set. So I hope you enjoy our paper and you go read it. So yeah, and also go play with the data. So have a good day.
Okay, thank you. So I think we have time for one small question. Anyone?
So I was curious about the latency time. So you mentioned the time for training, but what's the time for actually recommending?
Can you hear me? Hello?
Yes, not very loud, but I can.
Oh, okay. So for the inference time, right now we know that the bottleneck is not at the inference time, but with the database, with the traffic that we have. So that's where the next optimization will be done. But for the inference time right now, it's not where we want to optimize further. Maybe in the future if it becomes the bottleneck, but it's under a second. It's maybe in the 100 of milliseconds right now. I don't remember the exact number.
Thank you.
Okay. So I guess if there are other questions, I invite you to try to contact Jean-Philippe in the platform. So we'll move on to the next paper. So thank you, Jean-Philippe, again. We'll move to the next paper, which is entitled HeroGraph, a heterogeneous graph framework for multi-target cross-domain recommendation. It will be presented by Kang Kui. Kang, go ahead.
Mr. Editor, you can just play my video.
Do you prefer to play the video?
Yes.
Okay, just let me try to do that here.
Hello, everyone. Welcome to my presentation. Today, my topic is HeroGraph, a heterogeneous graph framework for multi-target cross-domain recommendation, and I'm from China. The contents are divided into 4 parts. First, let's look at the introduction. Single domain recommendation is a common task in recommendation systems. In such a kind of situation, we only have one kind of data, such as movie or book. And this kind of recommendation often faces problems such as sparsity. During the development, cross-domain recommendation seems to be a promising way to relieve such problems. Its basic idea is to transfer the information from source domain to target domain, such as from a movie to book. And cross-domain recommendation will relieve the target domain's sparsity problems and so on, and to improve its performance. Besides, cross-domain recommendation also has some disadvantages, such as this process is not vice versa. Next, let's look at 3 tasks about cross-domain recommendation. First one is single target cross-domain recommendation. In this task, we only need to improve the performance of target domain, such as we use information from A to improve the performance of B. Second is dual target cross-domain recommendation. We need to improve performance of both source and target domains simultaneously. The third one is multi-target cross-domain recommendation. we need to improve performance of all domains simultaneously. Next, we look at the motivation and the contributions of our work. The motivation 1 is about pairwise relations. Previous works generally construct pairwise relations between domains. If they directly handle n domains, there will be at least say n2 relations. It will become too complicated for them to handle multiple domains. Next is about preoperations. Previous works prefer relieving the sparsity issue by extra information or overlapping users. This leads to a lot of preoperations, such as feature engineering and finding common users. And we have 2 main contributions. First is about the shared graph. We propose to introduce a shared structure to model information from multiple domains, such as graph. And this structure can greatly simplify the cross-domain, cross-modeling process. Next is about the neighbor aggregation and sparsity. We propose to aggregate neighbors from all domains for users and items to reduce the sparsity issue. And besides, we also introduce recurrent attention to iteratively refine the aggregation. Next, let's look at some related work. First part is about target cross-domain recommendation. This paper was proposed in CIKM. It is the first work to propose the problem of target cross-domain recommendation. In the figure, we can see that it has a sharing layer which uses common users to transfer knowledge. It also introduces side information such as content, which needs pre-training. This paper is also about target cross-domain recommendation. It is based on users on 2 domains, and it needs to run mapping matrix to transfer knowledge. We can see that there is a matrix X, which links the 2 domains. The second part is about relieving sparsity. This paper is based on topic modeling, and it also based on side information, such as item metadata and user reviews to reduce sparsity. This paper is also based on common users and mapping function, such as this part is common user, and from here to here is a process of finding similar users. The last paper is also about relieving sparsity. It also based on common users and learning mapping matrix to transfer knowledge. Next, let's look at our proposed model. Our model is divided into 2 parts. First part is about the diagram of the hero graph. Our model is divided into 5 layers, and the first one is a shared layer. In this layer, we construct a shared graph. This is a heterogeneous graph constructed by users and items from all domains. In this area, we can see that a user in domain A put many items in from all domains, such as domain A, domain B, and domain N. Next is within domain modeling. We just use 1 hot embedding. And each user and item will be represented by a vector. Then is a cross-domain modeling process, which is represented by the red arrows. This modeling will transfer knowledge and reduce sparsity by neighbor aggregation. Next, let's look at the recurrent attention, which is proposed to handle this part, the center layer. In the recurrent attention parts, we will use Q, key, and V to compute the output. Q is a node vector, key is a neighbors vector, and V is an embedded neighbor representation. The formula is here. The recurrent attention weights are computed by Q and K. In this part, this is a loop, and we will iteratively communicate the attention weights. The final output of neighbor aggregation is over here. And we will repeat multiple times to refine the process of neighbor aggregation, such as from the head to tail and from tail to head. It is a complete loop. Then we will see the experiments. First is about our dataset. We choose 6 datasets from the Amazon dataset and divide them into 2 groups, which means each group has 3 domains. The first experiment is about hyperparameter optimization. This figure shows the optimization about hyperparameters such as dropout rate. Please pay attention that we choose global optimal parameters, such as we choose dropout rates is 0.2. This strategy will affect performance, but at the same time, it will reduce the amount of parameters. This figure shows the performance of baselines and our models. We can see that our model achieves the best overall performance. On task 1, our model is very good. On task 2, our model not as good as enough, but also competitive with the best baselines because we use global optimal parameters, not domain-specific best parameters. It will affect performance. The last slide is about sparsity and recurrent attention. First, we divide a sparse set and select items that appear in the test set no more than 5 times. This is a sparse set. And we conduct experiments on this set. We can see that the sparser the data set is, the more effective the model is. Then we will see the recurrent attention. We can see that attention 2 is overall better than others. And there may be overfitting, and the number of cycles should not be too many. Thanks for your listen.
Okay then, questions, anyone? I have a quick question, maybe. Do you have a way to control how much of each domain contributes to the model? I mean, can you control? You have 3. Your examples have 3 domains, right? Can you adjust the model so that it gives more importance to some domains instead of others?
Actually, I didn't have this part in the paper. I just added the results from different parts of the model directly. So I think it is a future work. And also, the weight can be updated adaptively.
Okay,
it was studied in the field. Thank you, editor.
Okay then, so I guess we're a bit tight on schedule, so we'll move on to the next presentation. So which is incremental graph of sequential interactions for online recommendation with implicit feedback, presented by Murilo Schmidt. Okay, Murilo, go ahead.
Hello, everyone. Can you hear me?
Yes, perfectly.
Just a second. Okay, can you see my screen?
Yes.
So thank you very much for the introduction. My name is Murilo Schmidt. I'm a PhD student at the Federal University of Paraná in Brazil, and I'll be presenting the paper, Incremental Graph of Sequential Interactions for Online Recommendation with Implicit Feedback. So the main goal of a recommender system is to recommend items to users based on their preferences in order to improve their interaction with the system. So collaborative filtering is an effective technique to solve this problem, in which the prediction of an unknown user item preference is inferred considering past user behavior, which is extracted from explicit or implicit feedback. And traditional collaborative filtering approaches, such as neighborhood methods and latent factor models, usually adopt batch data processing. And although these collaborative filtering approaches are generally effective in predictive capability, they usually operate under the assumption that training data is always available and is static, so you can always use it for model update. And another problem is that temporal sequence can be disregarded. Assuming that in real-world systems, time-dependent data is generated continuously at unprecedented rates, it becomes impractical to update these models as new data is generated. So learning and updating a model with one or few examples is preferable and even required in some cases. So to that end, incremental algorithms can be used. They allow to treat data as a data stream, so feedback is continuously generated, and feedback can then be incorporated into the model as data arrives. And after the model is updated considering the current example, the example can be discarded after they are processed. So considering this scenario, we propose to incorporate implicit user feedback into an item graph in incremental fashion. So the item graph operates under the assumption that user behavior can be extracted from the sequence of user interactions as time progresses. So to capture this behavior, edges are continuously included in the graph and updated according to the sequential user interactions. And then for each incoming feedback, a directed edge connects the last interacted item to the current interaction, such that the frequency in which the sequence interaction occurs is reinforcing the weight of the edge. So we compare the results with an incremental matrix factorization method available in this paper called incremental stochastic gradient descent. It's an algorithm designed to work with implicit feedback, and we evaluate our method using frequential evaluation and show that our recommendation strategies present competitive results. So some preliminaries for the proposed approach is an item recommendation problem under our data stream framework. So data is generated continuously and an unprecedented order and rate. So we aim to incrementally learn user behavior from implicit feedback as time progresses. And we want to include new incoming users and items continuously. So as I said, we operate under the assumption that the sequence of interactions can be useful in modeling user interest. And then we aim to generate recommendations based on past interactions. So the sequential interactions between users and items are incorporated in a directed graph, where nodes represent items, edges represent user interactions. The direction of the edge represents the order in which the items were visited. So for instance, consider an edge from I to J. This edge is included in the graph if a given user U interacted with item I at time t, and then at time t+1 interacted with item J. And then each edge has an associated weight inversely proportional to the frequency in which a transition is made by users, implicitly measuring the relevance of the edge. In other words, more frequent these sequential interactions happens, the lower the weight of the edge is and more attractive it is to recommendations. So here, excuse me, we have a toy example in figure A. So if we consider a given user interacted at some time with item 5, and then he interacted with item 0, an edge from 5 to 0 is created to incorporate this interaction. And then considering that the same user, after interacting with item 0, interacts with item 1, we want to incorporate this information in the graph. So in item C, in figure C, excuse me, we can see that the edge already exists and we update its weight to reflect this current interaction. So more formally, we have a weighted directed graph. V denotes the set of nodes, E the set of edges. Each edge has an associated weight W. For each user, we store the sequence of interactions ordered according to time. So for convenience, we also store the last interacting item by the user. And then, as I mentioned, we model user feedback as a data stream, where each observation is defined as this form, indicating that user U interacted with item I at time t. And the graph is updated considering the current observation. So since we want to continuously include new coming users and items, for each observation, 4 scenarios are possible. So user and item can both be unknown by the system. So in this case, we include them in the system and we add this interaction in the sequence of interactions of the user. A user can be unknown when the item is known. In this case, the user is included in the system. The interaction is stored for the user. And given that this is the first interaction by the user, there is no change in the graph. And then a user can be known when the item is unknown. In this case, the item's node is created for the item in the graph. And in these scenarios, user U has already interacted with at least one item before. So we take the last interacted item by the user and create an edge connecting this item to the current item in the observation and initialize the weight equal to 1. And finally, both user and item can be known by the system. So 2 scenarios can happen here. The current sequential interaction can be already known. In this case, we update the edge weight based on this equation that multiplies the current weight for a parameter rho that controls the impact of the interaction in the edge weight. And if this is the first time such interaction happened, we simply include the edge in the graph with weight equals to 1. Then to evaluate the information included in the graph over time, we tested a few recommendation approaches using as baseline the in-degree centrality, which basically an item is going to be recommended for the user if it's a popular item. This recommendation method does not distinguish users and simply recommend the most popular items according to the graph. So considering that new common users are constantly being included in the system, we want to assess the influence of the most recent interaction. So in this case, we filter candidate items as successors to the last interacted item by the user. And we test 2 different approaches. Again, the in-degree centrality and edge weight based on the last interaction. So this approach values the amount of times sequential interaction happens. And then we want to check long-term interest. So we consider the entire sequence of interactions by the user. And for that, we test 2 different approaches. Again, edge weight, considering the entire sequence of interactions. And what we call path count. In this case, an item is going to be relevant if the item is successor to several items in the sequence. So assuming that user preference change over time, we expanded the 2 previous approaches to, instead of considering this entire sequence of user interactions, to consider our most recent user interactions. And then we evaluate the parameter R in subsequent experiments. So to evaluate the proposed approach on a data stream, we need an appropriate protocol. So we use the deprecation evaluation protocol as proposed in this paper. So for each incoming event, which has this form, if U is a known user, we use the current model to recommend items to the user. Then we score the recommendation list. We update the model based on this current observation and proceed to the next observation. And then accuracy is measured through hit rate at the end at cutoffs 1, 5, and 10. We use two data sets from movie domains, Movie Lens and Netflix. These are explicit feedback data sets. So to simulate continuous implicit feedback, we dropped ratings below 5. Events are sorted chronologically. And for the Netflix dataset, we randomly selected 10,000 users and used their ratings. So accuracy, we compared with the incremental SGD. We use the first 20% of it, since they are already recording full time. We use the first 20 dataset to build the models, and the remaining 80% were used for incremental evaluation and learning. So besides accuracy, we also measured the average time to update the model, and average time to generate recommendations. So to update the edge of the weight, we set HOI equal to 0.9 and use the library network X for graph manipulation. So here in the results, we have first the impact of parameter R in the accuracy of algorithms, edge weight, and path count. So as you can see here for movie lengths, for both algorithms, as we tend to decrease R, the hit rate increases for both algorithms until reaching a peak, 3 for edge weight and 5 to path count, before dropping off. This point right here is based only on the last interacted item we defined as edge weight Li. And for the Netflix, we can see that things are more stable, but similarly, they tend to slightly increase as we decrease R until reaching a peak and then dropping off, especially for the path count algorithm, since we lack sufficient data to distinguish candidate items. So recommendation time is associated with R, since the algorithms iterate the successor to the last R nodes. So we can decrease recommendation time by lowering R. And then for overall results presented next, we set R equals 3 and 5 to movie lengths and 7 and 13 to Netflix. Here we have overall results. The best results are highlighted in bold. So for both data sets, we can see that considering the edge weight, that is the frequency of a sequence interaction, presents the best results for both data sets. We can see that all graph-based methods outperformed incremental SGD. We can see that for all algorithms, update time is not very meaningful. We can also see here that the two approaches based on the entire sequence of interactions becomes unfeasible time-wise, which can become impractical in a lot of applications. But we can also see that by considering only the most recent interactions, we can both improve the accuracy and also reduce the recommendation time. So every graph-based methods outperform the graph baseline. The four best algorithms are edge weight and path count R, which suggests the potential of incrementally including information from sequence interactions in the recommendations. Both ISGD and graph-based methods achieve competitive update time. For the graph-based methods, updates consist in inserting a new edge or updating an edge weight. And all algorithms, but those that consider an entire sequence of interactions, present acceptable recommendation time. And a consideration is that ISGG is more efficient in terms of space complexity since it grows linear to the number of users and items. So here we have a moving average for both for all algorithms in both datasets. We can see in moving lanes that all algorithms behave similarly, and that the edge weight significantly outperforms other methods. And for the Netflix dataset, this technique generally outperforms every other technique. So in conclusion, we propose an incremental graph of user interactions using implicit feedback under the assumption that this user behavior can be inferred from the user's sequence interactions through time. We tested 2 different approaches on 2 movie domain datasets. And using the frequency evaluation, we saw that the graph-based methods outperformed the matrix factorization technique. And the best results were achieved by considering the weight of the edge, connecting the most recent user interactions with the candidate item. So as future work, a limitation of the proposed approach is that it requires sufficient data from several users. We also aim to update edges according to user sessions, include loss of edge relevancy through time, explore different ways of generating recommendation, and to compare with other incremental algorithms using the frequency evaluation. And that's it. Thank you very much for your attention. I would like to apologize for there are some chairs for not sending a recording of my presentation. And that's it.
No worries. Thank you, Murilo. It was a great presentation. So, any questions from the audience? I actually have quite a few questions, but I think I'm going to ask them in some other time, okay? I'll just ask one quick one now. Do you have software? We have this implemented in what kind of software?
Implemented in Python.
Okay.
With Network X for graph manipulation.
Okay. Do you have the software publicly available somewhere?
Not yet, but if you reach to me by email, I can share it.
Okay. Okay, great. So I guess we'll move on to the next presentation, entitled Recommending Accommodation Filters with Online Learning. The presenter is Lucas Bernardi. Okay, welcome, Lucas.
Hello, can you guys hear me?
Perfectly well. Okay, go ahead.
Yeah, push my screen. Yeah. All right, I hope you can see my screen. Welcome to my session. My name is Lucas Bernardi. I am a machine learning scientist in Booking.com, and I'm presenting this paper entitled Recommending Accommodation Filters with Online Learning. So let me just start. As you may know, Booking.com is a two-sided marketplace where guests can search and hopefully find also and book and stay accommodations all around the world. To do so, they typically give us very little amount of information about their preferences. For example, they give us the destination, which can be a city, but can also be a country and even a whole region like Alps or Patagonia or Caribe, why not? Much better. And then they can also give us the dates, but some people don't really give us the dates and some other details. Even in the best case scenario where they fill in the whole form that you can see here, still the amount of information is very little. And this leads to a very large amount of results in the search results page, easily reaching 600 or hundreds of options that users would have to analyze one by one. Of course, this is not ideal and hurts everyone in the marketplace. Because of that, just like many other e-commerces, we introduce the filter capability, which allows users to express more specific search criteria or more specific preferences preferences by hopefully narrowing down the long list of options so they can find what they want. But unlike most e-commerces in Booking.com and maybe in general in travel, the amount of available filters is really, really large. And that's because the variety of types of accommodations is very large. You can think of hostels, hotels, agroturismos, for example, in Italy, villas, apartments. You can also think of different types of travelers, families, business travelers, solo travelers, couples, and also, I don't know, you can think of different types of destinations that might require different services. So in general, large variety of accommodation types, which leads again to more a large amount of filters, which puts us against, back to square zero, because then users needs to analyze many different filtering options. Now, when I mean that there are many options, I mean there are many. As you can see here, this is a search results page that I had to split actually in 3 parts to be able to show you all the filters. I swear there aren't any repeated filters here, and actually some of them you could still extend to see even more. So it's a rather long list, which definitely fits the very purpose of filtering. So this motivates the work of this paper, which is to come up with a short list of very relevant filters. Relevant for the current query, for the current user, and that's sort of the focus of this paper. In a sense, we consider this a third contribution of the paper, which is to an application of the recommended system field to a new domain, which is simply the filters. Now, in principle, this is just an application of the recommended system field, but there are a few challenges that make this problem a bit more particular, a bit, put it a bit aside from more classical recommender systems. First of all, feedback is a rather challenging aspect, and I could spend hours talking about this one, but essentially, pretty much everything stems from the fact that users' primary goal is not about filters. They are not looking for filters. They are not really willing to book or to purchase filters, and they are after, in our case, accommodation. So what that means is that to tell whether a filter is useful or not, we must rely on very noisy user interactions, which are scattered across the platform in many different, devices and many different, events or situations. So, getting utility for the filters is a rather complicated issue, and there's quite a bit of discussion about it in the paper. The second challenge is UX consistency. This is less of an issue in more traditional recommender systems, because if you refresh the recommendations every time the user clicks search, that's not such a big problem for our customers, but you cannot really do that with filters, because users interpret the filters as part of the, yeah, I was hearing someone. So I was saying that the filters are interpreted as part of the user interface, and of course, as such, you don't really want it to change very quickly. And this is a very interesting problem, actually, because it introduces a bit of a trade-off between data volume and consistency, because the more you sample, the more you recommend, the more data you get, but also the more inconsistent the user experience is. Now, on the other hand, if you simply sample once, the experience will be super consistent, but you're going to get much less data. And it's also a bit of an engineering challenge, because we need to remember the recommendations we make to our customers. We can't just spit recommendations and forget about it. And that's, we need big key value stores that are fast both at writing and at reading, and that's a bit challenging. And the third aspect that is very challenging to have a strong influence in our architecture is non-stationarity. And non-stationarity is also a rather common problem in most recommender systems, but in our case it's exaggerated, mainly because of the way filters interact with each other. In general, you can imagine external events like coronavirus, for example, had a strong impact on the utility of our filters. For example, when coronavirus struck on Europe in around February, March, we saw the free cancellation filter to become super important. And after a couple of months, it went down. And then, for example, hygiene filters or safety related filters became much more important. That's an example of how the utility changes all the time. But another one, which is very interesting, is the fact that we are constantly trying to come out with new filters, because this is a very important tool. So new filters compete for the attention of the user. So when we introduce, for example, family-friendly hotel filter, which shows only hotels which have some friendliness for the families. Other filters actually lost a lot of utility. For example, those filters about facilities for families like babysitter, indoor playground, and maybe crib and stuff like that. So from the point of view of these pre-existing filters, the utility really changed a lot overnight, and that's a very extreme case of non-stationarity. All right, so this is kind of the three main aspects that drove our architecture. So we propose to use online learning in the paper to address this business problem. And when you want to use online learning, you sort of assume that you have some sort of stream of data that has this shape, context, filter, utility. The context simply features about the query and the user. The filter is the filter ID itself, but also some features about the filter, like how many properties match that filter. And the utility is this abstract thing that we don't really know what that means. Unfortunately, the user interface is not ready to really give you this data in this shape because users behave in a very messy way. They go back and forth the search results page. They like to open many tabs. They like to search and go for a walk and 2 hours later come back. So they do many weird things that you are not ready to process in principle, at least not in the user interface. And that makes it really hard to go from user interactions to a feedback stream that we can actually use for training a machine learning model in an online fashion. So in the paper, we propose this architecture where we introduce 2 important components. One is the instrumentation layer, which offers a feedback loop protocol. This feedback loop protocol is simply a set of 4 primitives that you can see here, and that make it very easy for the user interface to map user interactions to invocations for the instrumentation layer. So this feedback protocol is essentially the language that the user interface software can use to map user interactions into the instrumentation layer. Based on this invocation, the instrumentation layer will keep track of the state of the recommendations using its internal state machine, and will take care of producing a very clean and very structured and very well-formed feedback stream that can actually be used to train an online learning model in an incremental fashion. The instrumentation layer is also responsible for the consistency of the user interface, so it's deciding when is the best moment to actually make new recommendations or when is the moment to reuse the recommendations that were made maybe a few seconds ago. In the paper, we discuss quite in detail the feedback protocol and the instrumentation layer, and also the architecture of the online learning system, which is actually based on a distributed system and what we call replicated SGD, which you can probably guess is SGD, replicated in many nodes at the same time. But I invite you, of course, to read the paper to know all the details about it. This is essentially our main contribution, basically an architecture that allows to produce data that is ready to train an online learning model in an incremental fashion from very messy interactions of our users with the user interface, and basically freeing up the user interface from any need to keep track of the state or any complex logic. Now, I don't have time to go into any of these components, but I want to show you at least one experiment that we ran, because of course we implemented this whole thing and we put it in production in Booking.com, which is rather challenging. And I want to show experiment number 2, where we're trying to tell whether this model is adaptive, because in the end, what we're after here is to produce an adaptive system that can pick up new filters and that can adapt to changes in the utility of the filters. Now, testing adaptivity is a bit challenging because you not only always know when the utility of the filter actually changed. So what we did is we kind of give a shock in the utilities by allowing automatic traffic from non-humans to hit the model. So Booking.com has a lot of traffic coming from non-humans. It's a crawler, scrapers trying to get pictures, reviews, scores, prices. Usually we filter them out. We don't let our models to be hit by them. But in this case, we allow them to hit our model because that actually changes a lot the utility of the filters. And then we disable that bug and we see what happened. So in this chart, you can see on the x-axis the time, that's 8 weeks, that's the duration of the experiment. On the y-axis, you can see the CTR after using a filter. And this is the delta actually with the baseline. The baseline is a supervised learning model, very static with many business rules. You can read more about it in the paper, but it's a quite strong baseline. And of course, if it's negative, it's bad, that's red. If it's good, it's green, that's positive. And you can see the model starts already on the green side because this is already warmed up model. You can see how we warm up the model in the paper, but here it's already trained for a couple of weeks. And then in book number 5, we open the bot gate, and we can see that the utility, or actually the click-through rate, went down really, really bad, all the way into the negative part. And that day was, okay, that's enough, 1 week. Then we close the gate of the bots, and you can see that produces a second change on the utility of the filter, and you can see how the model really recovered, came back to the previous level, and then actually took off even higher. So this is considered in our interpretation evidence that the system is actually capable of adapting to changes in the utility of the filters in our case. There are more experiments in the paper. We also show how the log loss change and other metrics. So I encourage you to take a look to learn more about it. I think I'm running out of time, so that's it.
Okay, Lucas, thank you for your nice presentation. Very interesting. Any questions? Don't be shy.
It was a very clear presentation.
It was very clear, yeah.
No questions.
I have more of a comment than a question. That is, I think it's really nice, a really clever idea to use the bots to have to control the experiment. It was very interesting.
I must clarify that they use filters. They actually filter to get the specific data. But they do it in a very different way than humans do. That's why we know that the utility will change. Yeah.
Okay, so we're a bit behind schedule, so maybe we can move on, and everyone can contact Lucas during today, maybe tomorrow. I don't know. So next presentation, and congratulations and applauses, of course. The next presentation is debiasing few-shot recommendation in mobile games. The presenter is Sahar Asadi.
Yeah, thank you.
Hi.
Do you hear me well?
Yeah, perfectly.
Okay, great. Let me share my screen. Cool. Yeah, hi, my name is Sahar, and I am AI research lead at KIM. Yeah, so in this presentation, I'm presenting our work, debiasing few-shot recommendation in mobile games. And this work has been done together with my co-authors, Lele, Matteo, and Michael. Mobile games are becoming more and more popular, and designing mobile games comes with its own challenges. So the screen of mobile has a very small space to put a lot of different options in the game for the players. And the players spend a very little amount of time every time that they come and they want to try out the game, especially if it's a casual game. So here is where recommender systems come into the place, because we don't want to overload the experience of the user with tons of different options and with different offers from the game, and to give them a very bad experience. So the goal by applying recommender system is to surface more relevant options to the player in order to improve their experience. Here you can see a couple of examples from our mobile games at KIM. On the left, you see game live ops, where we have a few shots of showing recommendations to the user, including the rewards and different side game challenges in Candy Crush Saga. On the right, you see another example from our game Candy Crush Soda Saga, where we show daily gifts to game players, and here we have a single shot of choosing an item to show to our user. So often, especially in games, the need for personalization doesn't exist from day one, though there is usually already a somewhat acceptable heuristic policy in place from day one. And existence of such a heuristic policy leads to different biases into the data sets if we want to introduce recommender systems. Example of these biases are positional bias or exposure bias. And without intentionally correcting those biases, the final recommendation could be misleading. And in our experience, so there hasn't been so many previous works that explicitly modeling for those biases. So if we look at the challenges, first we have a few shot exposures. And this means that any change in the choice of items can have a large impact on game dynamic. And this can lead to short feedback loops compared to other applications such as e-commerce. And because of this, also we have highly imbalanced data. And the data is very biased due to existing heuristic policies. One thing to mention is that collection of randomized exploration is not a preferred option because this can be quite intrusive to user experience. And finally, the player preferences changes quickly due to changes in the game dynamic and the player context. And that means that as a result, models get outdated sooner in real-time prediction. Considering those challenges, we propose an end-to-end debiasing few-shot network. Here I call it DFSNet. And we discuss an approach to benchmark the trained model offline. We highlight challenges of online recommender systems in the context of mobile games. And given a use case, we demonstrate how to monitor, evaluate, and iterate on the model in controlled A/B test setup. So let's have a look at our model. First, let's just remember that we want to rank K items, capital K here, where the item K has a value of VK for a player in order to maximize the expected click value. For simplicity, we sort the items based on their values. So items are indexed based on their values. And we focus only on one shot case, but of course it can be generalized to multiple shots. When we are collecting data, so we collect data over a span of n days. We collect both behavioral features and contextual features. So behavioral features, for example, we have the total number of game rounds played during this n days. And contextual features gives us information prior to the moment of the trigger where user gets exposed to the item. So example of that is the latest inventory state of the player. And finally, we use a binary label to annotate whether the item has been clicked or not. So our model is composed of three components. First, we have a preference predictor, which estimates the probability of a player clicking item K if this item is exposed. Then we have confidence predictor, which is an approximation of the confidence we have for this predicted click probability. And finally, we have meta ranking, which ranks the items by calculating a score using the preference predictor, confidence predictor, and the actual values of the items. So let's have a look at our modeling. To train the model, first we split the data into mini batches. And for each mini batch, we partition that mini batch to K partitions. Here again, capital K. So in this case, for instance, we have 5 items that we want to choose from, and we have 5 partitions. In each partition contains only samples of users exposed to that particular item. And because these partitions are quite imbalanced, we apply a minority sampling to balance our samples. And then we calculate the loss. So in the next step, we have the confidence predictor. First, we apply a filtering in our features to remove features that are used in heuristic policy, if there is any that we are aware of. And with that, we want to avoid memorizing heuristic. Then, given that samples that we have, for each of the 5 Ks that we have, we partition X into 2 sets, one including samples, one including users where they have been exposed to item K, and the other one is the negation, which includes users that they haven't been exposed to that item. And again, similarly, we do minority sampling, and the two losses are jointly optimized during the training. And finally, we have the meta ranking. Meta ranking is using the predictive confidence, the probability of clicking, and the values from the items. So what it does is that basically weighs in the confidence and the click probability in order to rank the content. So where we split the condition based on whether we have a high confidence and high click probability, and the other way. One thing to mention is that remember that we said the items are sorted based on the values and indexed based on the values. The thing is that we don't want to have an intrusive and drastic experience change for the user. So in order to avoid that, we also define a threshold, a deviance threshold. What it means is that, for instance, we don't want to show to a user that is used to seeing a very large item, a small one, or the other way around. So we limit the changes between the indexes of the items. So let's have a look at the experiments and the evaluations. We took a use case from our game Candy Crush Soda Saga. Here we have 5 items to choose from, and we want to choose one that is maximizing the click value. We are looking at 22 million samples, and we take 1% of that for testing. And the data is collected over 28 days, and we have 48 features. During the training, we chose to focus on looking at ROC curve, which is a more stable metric to look at given the nature of our problem. And what we are seeing both for confidence predictor and the preference predictor is that the generalization ability of the model improves during the training. And when the training is finished, we start looking also at precision and recall. After our model is trained, we look at the changes in the policies. So here, this is a player transition matrix. So if we look at cell J and I, this cell contains share of users who were supposed to be exposed to item J based on the heuristic, but now, given the DFS-net recommendation, they are recommended to be exposed to I. So if we look at the non-diagonal values, which is the changes that we have, we see that 7.4% of our users see a different item than the heuristics. And also, if we look at these corners of our graph, which is the extreme deviances that I mentioned, we also confirm that we are not making drastic changes to player experience. So if we want to go deeper to analyze our model and get insights about our performance, we can also start looking at click preference and confidence probability together. I'm not going through these slides, but I can tell you some of the findings. So we found out that clicking tends to be a rare event. We also found that the majority of exposures comes from the item 1. And we also saw that, so if you want to analyze the confidence that we have in the items, we can look at the shaded area or the samples that they are outside this shaded area. So the next step was that whether we are happy to put this in production. And for that, we made a proxy effort. We collected a subset of our items recommended by heuristic and DFS-net with the same value. And we measured the click, average click rate and average click value, and we saw an uplift in those values, which was a green light for us to now go and try out an online test. So now I want to show you the online serving and the evaluation. The very first thing is that, so we made sure during the offline that we are using the streamed batch data, which is coming from the same values that we are looking at during the inference time. But before running, putting our model in live, and into production, we just wanted to do a monitoring of a few metrics in an A/B test on a small group. And here we are considering two aspects. So we are looking at the scale of the impact, and also we want to see how this impact evolves over time. So let's have a look. So we ran an experiment over 28 days. And here we are looking at the metric of the ratio of players that get a different item than heuristic. Remember that I mentioned that during the offline, we saw an uplift of 7.4%. So in online, the red line, we also see that our model, when it starts deploying, is gaining a momentum and is catching up with the offline performance. So it seems that we had a relatively good metric to look into, but we also see a drop. And this drop is actually coming from the fact that I was saying that we have short feedback loop, and it shows a need for reiterating and retraining model on new data. One thing to mention here is that we see this slow slope here. And the thing is that while our features are populated and getting completed for users, during this time, we use a fallback solution, and that is our heuristic. So if we go a bit deeper and look at the model impact, so we look at when we are updating our model in over the 14 days, and we look at the player transitions. So this is the offline one that I showed before, and this is the one for these 14 days. And what we see, if we look at the diagonal values, which is where both heuristic and recommender, they show the same value, they suggest the same. We see that that is stronger in the online one, which means that our online model is more conservative. But that is expected until we reach here, because it's some of the results are using the fallback, but after that is going to catch up and show a similar pattern as here. We also looked at some user dynamics. We looked at the uplifts of click ratio, counts, and uplifts in click values. We see a drop in click counts in two of the items, but at the same time, we see that this is compensated by increase in click values of the other items. And finally, we get to the last question, is that when to basically retrain our model. So what we do is that we keep monitoring precision and recall, which are more sensitive metrics on daily basis. And we look at over the period that it is trained. And here you see a comparison between day 24 and day 28. So the green bars are related to online, and the red bars are related to the offline one. And we see that as the model starts drifting, the performance of the online model starts dropping in most of the items and pushing down compared to offline. And this is the time that we know it's time for retraining of our model. So to summarize, we proposed a method that aims to avoid traditional biases. We are also suggesting some offline proxy metrics. We are looking at the real-time predictions, and we also discussed a bit about serving and monitoring and the online solution. And for future works, we are exploring the choices of metrics that constitutes a better proxy of the model for online performance. And we are looking for long-term metrics that they can proxy business metrics. We are also looking at model explicitly the interactions between different features to eliminate the implicit feedback loop. And finally, we are interested in trying out online reinforcement learning to replace the model interaction. Thank you.
Thank you, Sahar. So we have time for one quick question. Anybody wants to ask something? You can turn on your mic and your camera if you wish and make a question.
I have a question. It's a bit dull here though. Hey, thanks for the presentation. It was really good and really complete work. And I'm very curious about the confidence estimation. I honestly didn't quite follow how you compute that. So if you can maybe give us some pointers about what is the intuition behind the confidence estimation, that would be pretty useful for me at least. For example, how does it
So,
connect with upper confidence bound estimations and stuff?
So the confidence is basically telling us if the user has seen before, has been exposed before to this item, kind of. So it's kind of like an upper bound, and it's a confirmation. So we feel comfortable to show that to the user if the user has been exposed to before and has been clicking that item. And if it's not, then like we have a lower confidence.
Oh, it's more of an estimation of the risk of.
Yeah, exactly.
Of that. Okay, got it. That's perfect.
Exactly.
Thank you. It's very useful.
Okay, so we move on to the last paper of the session and the workshop. The last paper is Combining Models for Better User Satisfaction in Video Recommendation. And it's going to be presented by Karel Kupil. So go ahead, Karel. Thank you.
Thank you. Hi, my name is Karel Koupil. I'm a senior product manager of recommender systems at Seznam CZ. I'm going to tell you about a multi-criteria optimization in a video recommendation. Let me briefly introduce our company. Seznam.cz is the biggest internet company in Czech Republic. Our homepage with nearly 3.5 million unique users daily is the most visited Czech web page. In peak hours, we experience roughly 4,000 requests per second. Our services include a free email, search engine, map service, TSP, TV broadcasting, web browser, and many other content sites and applications, as you can see at this slide. Like other content providers, we also strive to deliver the most relevant content for our users. Until last year, we had employed only click-based signals, ignoring post-click user behavior and rewarding more clickbait headlines. Then we decided to incorporate user watch time, as it has proven to be a reliable metric of user engagement. Our main KPIs for user satisfaction is total watch time, TTS, that users have spent on a video service, together with CTR. Our objective is to maximize user engagement while still considering the number of video views. We address the problem of recommending videos for a content box, as you can see on the left side of the screen. We used a position feature as one of the signals in the training phase to mitigate bias arising from the presence of the picture at the first position. After a user clicks on the link, the video will start playing on the new page, as you can see. In our paper, we suggest two different approaches for modeling the relationship between click probability and watch time. We propose a solution based on generalized linear models suitable for an industry setting and evaluate our approach on live traffic. To maximize TTS, we need to attain a balance between videos with high CTR and the ones having a potential to gain high watch time. If one tries to increase TTS, for instance, by recommending very long videos without considering CTR, they may not be watched and final TTS may suffer. On the other hand, less relevant content might acquire high CTR due to, for instance, catchy title, which results in early exits, leading to loss of TTS as well. We consider several methods that consist of the single models that are combined and compared later to the compound ones. Logistic regression that considers clicks that resulted in played videos as positive examples and all the other ones as negative. A linear regression that training samples have labels representing ratios of consumed times for target videos with respect to their durations. Labels represent total watch time in seconds. And finally, Poisson regression, where labels are the number of watched parts sent by video player every 10 seconds. Having scored C and T from CTR and TTS models, we propose two following parametrized functions to get the resulting score. Once scores are computed, we sort recommendation candidates by the score, and top-end videos are then recommended. Both graphs on this slide represent the resulting score after the combination of CTR and TTS model. Hyperparameters alpha and beta are regulating the importance of CTR and TTS within a particular compound model. For increase in alpha compound models tend to put more weight on CTR and less weight on TTS. Similarly, for growing beta compound models tend to prefer CTR and put less weight on TTS. The main difference between A and B on this slide is its growing rate and different distribution of resulting scores. The former grows as power of alpha in C and power of 1 minus alpha in T. The latter grows linearly in T, but exponentially in C. Our data contains detailed information about user features and videos. Videos contain information about their source, several human-generated text, duration, and the time of publication. User features consist of information about previously watched videos, age, and a user profile that we created from the user history. A clicked video that ends up being watched is labeled with a positive label, click, and all remaining videos for a recommended list are assigned with a negative label, not click. We perform ABN tests on live traffic, and for each variant we then run AA test. We monitor metrics, CTR, TTS, averaged video duration, and the number of video views to mitigate the interference between variants. We train models in the incremental phase and only from the respective IBM variant. In the first experiment, we compare the performances of single models optimizing time metrics. The models perform differently regarding specific metrics. For example, line TTS boosts 4 times longer videos than the baseline CTR model. This results in the highest TTS and the smallest views. Views from benchmark models, line WR times VD model recommends on average shorter videos than line TTS, but still more than 2 times longer videos than baseline. The last model in this experiment was plus TTS that performed well in CTR and views, but scored the worst in TTS. The next 2 experiments display results of compound models. Since we wanted to improve user engagement, we the emphasis on moderately long and diverse videos, we concluded to use line WR times VD as a model representing T. The tables below displays results of a grid search over the subset of values of hyperparameters. As the experiments are performed during different time periods, we perform one more experiment that uses the best performing models from the previous runs. Since we did not succeed at maximizing all the metrics at once, we focused on maximizing TTS, and at the same time, we required only a minor drop in the number of views and CTR. Combining TS models with model optimizing CTR resulted in the best balanced results and increased TTS by nearly 28%. thank you for your attention. Now I would like to invite two colleagues of mine to help me with your questions.
Okay, thank you. So we have time for questions. Do we have any questions? So we don't seem to have anyone here wanting to ask a question. I maybe ask a question. Did this approach roll out to production? And are you currently using this in the services online?
Yes, we do. We use this in current production.
Mm-hmm. So my question is a bit more from the business perspective. Have you noticed? Well, you have made your evaluation that is more or less contained. Then have you noticed since then? Have you noticed a very relevant improved performance besides what you already had observed in your evaluation? I mean.
No, we don't do other experiments then,
Mm-hmm.
and we plan to do next course of experiments and at the end of this year.
Okay, that is great. Thank you very much. Applauses. So this was the last presentation. Before you leave, I would like to invite you again to submit a paper to the special issue on dynamic recommender systems and user modeling in UMUI. So the deadline for extended abstracts is October 30th, so you are all welcome to submit. You have more details in the website. I have left the link in the Wova chat, so if you want to check it. So thank you all for coming. It was a very nice workshop. Thank you to all the authors, to Sebastian, the keynote speaker as well. And thank you for coming. So I hope we can meet again sometime next year. Okay. Bye-bye.
Bye-bye. Thank you.